a city of stars. 1,000 galaxies bound together in a shimmering gravitational embrace is not where it should be. This is the Centaurus cluster, a cosmic metropolis teeming with worlds, nebulae, and the dying embers of ancient suns. And it is moving. Along with hundreds of its galactic neighbors scattered across a vast expanse of the southern sky, it drifts through the fabric of space-time at a speed of over 600 kilometers per second, a velocity that cannot be explained by the gentle, uniform expansion of the universe around it. This is not a random dispersal, a chaotic flight of matter into the void. It is a coherent, directed procession, a silent, inexorable pilgrimage toward a specific unseen point in the celestial sphere. This collective motion, this grand and mysterious cosmic river, has been given a name that echoes its enigmatic nature: dark flow. It is a current in the ocean of the cosmos, pulling vast flotillas of galaxies toward a destination that lies beyond the horizon of our sight, hinting at a source of gravity so immense, so powerful, that it must originate from something outside the known observable universe. The discovery of this phenomenon was not a sudden blinding flash of insight, but a gradual uncovering, a faint and persistent signal emerging from the background noise of the cosmos. Its first whispers were detected within the oldest light in the universe, the cosmic microwave background, a faint residual warmth that permeates all of space, a thermal echo from a time when the universe was a mere infant, just 380,000 years old. This ancient light, the afterglow of the Big Bang, is remarkably uniform on the grandest scales, a testament to the homogeneity of the early cosmos. But hidden within this uniformity are tiny, almost imperceptible fluctuations in temperature, minute variations that correspond to the primordial seeds of all structure. These fluctuations are the ghostly blueprints of the galaxies and clusters that would one day coalesce from the primordial mist, the faint whispers of gravity's first stirrings. It was by studying the subtle interaction between this ancient light and the modern structures of the universe that a team of astronomers led by Alexander Kashlinsky first detected the anomaly. They were not searching for a hidden current. Their goal was to measure the delicate motions of galaxy clusters relative to this cosmic backdrop. What they found was a puzzle that continues to challenge our most fundamental assumptions about the universe. Cluster after cluster, scattered across billions of light-years of space, seem to share a common unexplained velocity, a bulk motion that could not be accounted for by the gravitational pull of any known matter within our cosmic horizon. This observation strikes at the very heart of the cosmological principle, the foundational assumption that on the largest scales, the universe is isotropic and homogeneous, that it appears the same in every direction and from every vantage point. The uniform expansion of space-time driven by the mysterious force of dark energy should carry all structures away from each other in a predictable, even manner, like raisins embedded in a rising loaf of bread. The peculiar velocities of individual galaxies, their small local movements within the cosmic web, are easily explained by the gravitational tug of their neighbors. A galaxy falling into a massive cluster or being pushed away from a vast void is behaving exactly as our theories predict. But dark flow is something else entirely. It is a large-scale systematic deviation from this expected behavior, a sign that the cosmic river is flowing with a purpose guided by an unseen hand. It suggests that the distribution of mass in the universe is not as uniform as we have long believed, and that our observable cosmos, the sphere of light and matter that we can access, may not be the entirety of existence. The implications of this are profound, touching upon the nature of dark matter, the mysterious, invisible substance that provides the gravitational scaffolding for galaxies, and dark energy, the even more enigmatic force that is causing the accelerating expansion of space. If there are structures massive enough to pull on our corner of the universe from beyond the veil, then our current models of these cosmic components may be woefully incomplete. The search for the source of dark flow is a journey into the ultimate unknown, a quest that pushes the boundaries of both our technology and our imagination. Some researchers speculate that the pull may originate from colossal superclusters of galaxies or vast continent-sized filaments of dark matter that lie just beyond the edge of our observable horizon. These structures, perhaps remnants of the earliest, most chaotic moments of the universe, would be so massive that their gravitational influence could reach across the cosmic abyss, tugging on the very fabric of space-time itself. This idea suggests a universe that is far grander in its scale and more complex in its structure than we can currently detect, a cosmos with hidden geographies and unseen centers of power. The very existence of dark flow, if it is confirmed, would revolutionize our understanding of cosmic structure and evolution. It would provide clues not just about the distribution of mass in the universe, but about the overall shape and ultimate fate of the cosmos. It challenges us to look beyond the familiar shores of our cosmic island and to consider the possibility of a wider, more dynamic ocean, one whose currents are shaped by forces we are only just beginning to comprehend. The mystery of dark flow is not merely a question of astrophysics. It is a question of boundaries, a test of the limits of our perception and our theories. It forces us to confront the possibility that the universe we see is but a small illuminated part of a much larger, darker, and stranger reality. The investigation into this cosmic current is a story of intricate connections, a weaving together of disparate threads of evidence from across the entire spectrum of astronomical observation. The faint ancient light of the cosmic microwave background is not just a passive backdrop for this drama, it is an active participant. The photons of this primordial radiation as they journey across 13.8 billion years of expanding space are subtly affected by the structures they pass through. When they encounter a massive galaxy cluster which is filled with hot ionized gas, their energy is slightly altered by the cluster's motion. This is a phenomenon known as the kinematic Sunyaev-Zeldovich effect. It is a delicate and difficult measurement akin to detecting the faint ripple on the surface of a vast calm pond caused by a deep unseen current. By meticulously measuring these tiny shifts in the energy of the microwave photons, astronomers can infer the velocity of the clusters themselves relative to the rest frame of the universe. When this technique was applied to hundreds of clusters, the coherent signal of dark flow began to emerge, a collective motion rising above the random noise of individual galactic movements. This connection highlights the intricate, interconnected web of phenomena that shape our universe. The most ancient light we can see is carrying information about the most modern large-scale movements of matter. To confirm and explore these initial tantalizing findings, scientists have turned to other tools, other ways of mapping the vast, three-dimensional structure of the cosmos. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey, have become indispensable in this endeavor. These monumental projects have systematically charted the positions and distances of millions of galaxies, creating the most detailed maps of the universe ever assembled. Within these maps, the cosmic web becomes visible, a vast filamentary network of galaxies and dark matter punctuated by immense empty voids. By analyzing the motions of galaxies within this web, researchers can look for deviations from the expected Hubble flow, the uniform expansion of the universe. They can identify the peculiar velocities of galaxies, the small additional movements caused by local gravitational attractions, and search for the larger, more systematic currents that might signal the presence of dark flow. These observational efforts are complemented by the immense power of supercomputer simulations. These are not mere animations, but vast, complex digital universes built from the ground up according to the known laws of physics. Scientists can input the initial conditions of the universe as revealed by the cosmic microwave background and let these virtual cosmoses evolve over billions of years of simulated time. They can watch as gravity pulls matter together into filaments and halos, as dark matter forms the scaffolding for structure, and as galaxies ignite and evolve within these structures. By comparing the large-scale structures and flows that emerge in these simulations with the patterns observed in the real universe, researchers can rigorously test their theories. They can ask a fundamental question: Can the standard model of cosmology with its known ingredients of dark matter and dark energy naturally produce a phenomenon like dark flow through the chance alignment of structures? Or does the existence of such a large coherent flow require something new, some missing piece in our understanding of the cosmos? The simulations allow them to explore a vast landscape of possibilities, tweaking the properties of dark energy, altering the nature of dark matter, and even experimenting with different models of cosmic inflation, the hypothesized period of hyper-rapid expansion in the first fraction of a second after the Big Bang. The inflationary model itself is a key part of this intricate puzzle. It proposes that the universe underwent an exponential growth spurt in its infancy, an event that would have smoothed out any initial irregularities and stretched quantum fluctuations into the seeds of the large-scale structures we see today. If dark flow is a remnant of this primordial era, a fossilized current from the dawn of time, then it could provide a unique and unprecedented window into the physics of the very early universe. Another angle of investigation equally profound focuses on the expansion rate of the universe itself, a value known as the Hubble constant. This constant is currently at the center of a growing tension in modern cosmology, with different measurement techniques, one based on the early universe and one based on the late universe, yielding slightly different values. The presence of a large-scale flow like dark flow could potentially influence these measurements. If our local group of galaxies, the one from which we make our measurements of the late universe, is being pulled along by this cosmic current, it could subtly alter our perception of the universe's expansion, contributing to the discrepancy in the Hubble constant. Unraveling the true nature of dark flow might therefore not only reveal hidden structures in the cosmos, but also help to resolve one of the most pressing and persistent controversies in modern astrophysics. The quest is a testament to the relentless and multifaceted spirit of scientific inquiry, a multi-pronged assault on a mystery that lies at the very edge of our understanding, using every tool at our disposal to peel back the layers of the cosmic onion. This unexpected alignment of galactic motion, this coherent flow toward the constellations of Centaurus and Vela, has stirred a profound and unsettling curiosity that goes beyond the confines of academic astronomy. It is one thing to discover new objects or new forces within the known framework of the universe. It is another thing entirely to find evidence that the framework itself might be incomplete, that our cosmic home might be subject to influences from beyond its apparent borders. The central challenge for scientists is to distinguish between a genuine physically significant phenomenon and a mere observational anomaly, a ghost in the data produced by the inherent complexities of measuring the cosmos. Traditional theories of cosmic expansion, born from the elegant mathematics of the Big Bang model, predict a universe that is on the grandest scales fundamentally uniform. The initial explosion, followed by a period of cosmic inflation, should have smoothed out any large-scale directional preferences, leaving a cosmos that expands evenly in all directions. The existence of a preferred direction of motion, a cosmic axis along which vast structures are flowing, is a direct and powerful contradiction to this foundational principle. This has in turn opened the door to more speculative and more profound hypotheses. One of the most tantalizing is that the movement could be caused by the gravitational effects of structures that exist outside our observable universe. The concept of the observable universe is not a physical boundary, a wall at the edge of space. It is a horizon of information, a consequence of the finite age of the universe and the finite speed of light. Since the universe is 13.8 billion years old, we can only see light from objects whose light has had that much time to reach us. Any object farther away than that is for now, and perhaps forever beyond our sight. But there is no logical or physical reason to believe that the universe ends at our horizon. The cosmos beyond could stretch on for vast, perhaps even infinite distances. If there are colossal structures in that unseen realm, superclusters of galaxies, or concentrations of dark matter far larger than anything within our view, their gravitational pull could still be felt across the horizon, tugging on the matter within our observable patch. This idea fundamentally transforms our perception of the cosmos, suggesting that our universe is not an isolated self-contained system, but an open one in constant gravitational dialogue with a larger unseen reality. This line of reasoning naturally leads to an even more radical and mind-bending possibility, the multiverse. If our universe is just one of many a single bubble in a vast foaming sea of other cosmoses, then the gravitational influence of a nearby massive universe could potentially be the source of dark flow. This is a concept that pushes the boundaries of science into the realm of philosophy, as the existence of other universes may be fundamentally untestable. And yet the mathematics of some of our most successful and ambitious theories, such as string theory and the theory of eternal inflation, naturally predict the existence of a multiverse. In this context, dark flow could be the first faint empirical hint that these theories are not just mathematical fantasies, but are in fact descriptions of a reality far stranger and more expansive than we have ever dared to imagine. It would be the cosmic equivalent of ancient islanders who believed their island to be the entire world, suddenly noticing a persistent unexplained current in the surrounding ocean, a current that hinted at the existence of a vast unseen continent just over the horizon. The implications of dark flow thus extend far beyond the simple mechanics of galaxy movement. They challenge our deepest assumptions about the cosmos and our place within it. They compel researchers to reconsider the fundamental laws of physics as they apply to the largest of scales. Is gravity, as described by Einstein's general relativity, the only force at play, or could there be other long-range forces that we have yet to discover? Does the universe have a preferred direction, a cosmic downhill that has been imprinted upon it since the very beginning of time? As scientists gather more data from a new generation of advanced telescopes and space probes, they are engaged in a delicate and crucial task to either explain dark flow within our current understanding of physics, or to prove that we stand on the precipice of a new revolutionary paradigm in our understanding of the cosmos. This exploration embodies the true spirit of scientific inquiry, the relentless drive to peel back the layers of cosmic mystery, seeking answers to questions that probe the very nature of reality itself. The possibility that we are not entirely isolated, but are instead passengers on a cosmic river flowing toward an unknown and perhaps unknowable sea, invites a deeper and more profound examination of the very fabric of space-time and existence. The term dark flow itself is evocative, and it naturally suggests a connection to the other great dark mysteries of the cosmos, dark matter and dark energy. While the name implies a conceptual link, the phenomenon is distinct in its nature. Dark matter is the unseen mass that binds galaxies and clusters together, an invisible gravitational glue that constitutes the majority of the matter in the universe. Dark energy is the mysterious force that pushes space-time apart, driving the accelerated expansion of the universe. Dark flow, in contrast, is not a substance or a universal force, but an observed motion, a collective behavior of matter that seems to require an explanation that goes beyond the known distribution of both dark matter and dark energy within our observable horizon. As our universe expands, driven by the relentless push of dark energy, the space between galaxies stretches, and on the largest scales, everything should be moving away from everything else in a uniform manner. Dark matter, which is clustered in the halos of galaxies and the filaments of the cosmic web, creates local gravitational wells that hold structures together and cause them to move towards each other on smaller scales. But it is not expected to produce a coherent universe-spanning flow in one particular direction. The great riddle of dark flow is that it appears to be a motion that is superimposed on top of this cosmic expansion, a current that is running through the expanding sea. This raises profound and difficult questions about the interplay of these various cosmic components. If dark flow is real, it could provide a crucial new clue about the distribution of dark matter on scales far larger than we can currently map. Perhaps the cosmic web of dark matter is not as random and isotropic as our current models suggest. Perhaps there are superstructures, cosmic continents of dark matter whose gravitational influence extends for billions upon billions of light years, creating the cosmic equivalent of a large and powerful river system that guides the flow of galaxies. The evidence for dark flow, however, remains a subject of intense and often contentious debate within the scientific community. The initial observations, which were based on data from the Wilkinson Microwave Anisotropy Probe, or WMAP, were tantalizing, but also statistically marginal. Some researchers have argued with considerable justification that the observed signal could be an artifact of the data analysis, a subtle bias created by our own motion through the universe, or by the gravitational influence of known nearby structures like the Great Attractor, a massive gravitational anomaly located in our local cosmic neighborhood. The challenge of distinguishing a true large-scale flow from these more local effects is an immense observational and analytical challenge. It requires mapping the motions of thousands of galaxies with incredible precision and carefully subtracting all the known gravitational influences to see if any residual unexplained motion remains. Subsequent studies using data from the European Space Agency's Planck satellite, which mapped the cosmic microwave background with even greater precision than WMAP, have yielded ambiguous and often conflicting results. Some analyses have found continued, though weaker evidence for dark flow, while others have concluded that the signal is not statistically significant and can be explained by random fluctuations in the distribution of matter. The debate continues to stimulate new research and new observational strategies. Astronomers are now using a wider range of techniques to probe these large-scale motions, including detailed analyses of the light from distant supernovae, which act as standard candles for measuring cosmic distances, and the subtle distortions of galaxy shapes caused by the gravitational lensing of the cosmic web. Each new dataset provides another piece of the puzzle, another opportunity to either confirm or refute the existence of this cosmic riddle. As we delve deeper into the universe with ever more powerful telescopes and ever more sophisticated computer simulations, we may one day finally unravel this mystery. But for now, dark flow remains on the tantalizing edge of discovery, a whisper of a larger reality that continues to beckon us forward into the unknown, a siren song from the shores of an unseen cosmic sea. The first hint of this cosmic anomaly, as is so often the case in science, emerged not from a single dramatic discovery, but from a painstaking and meticulous analysis of the faint ancient light that fills every corner of the universe. The cosmic microwave background is a treasure map for cosmologists, its subtle variations in temperature encoding the entire history of the cosmos. When the WMAP satellite was launched in 2001, its ambitious mission was to create the most detailed map of this radiation ever made. The team of researchers who were analyzing this data were not initially looking for a cosmic flow. They were studying a much more subtle phenomenon. The kinematic Sunyaev-Zeldovich effect, a slight distortion of the microwave background that is caused by the motion of galaxy clusters. As the ancient photons from the cosmic microwave background pass through the hot ionized gas that permeates a galaxy cluster, they can scatter off the moving electrons, gaining or losing a tiny, almost imperceptible amount of energy in the process. This effect, though minuscule, allows astronomers to measure the velocity of the cluster relative to the cosmic microwave background itself, which serves as a fixed and absolute reference frame for the entire universe. It is a technique of immense subtlety and difficulty, akin to measuring the speed of a distant ship by observing the faint wake it leaves in the otherwise calm and featureless water. As the team of scientists meticulously applied this technique to the data from hundreds of different galaxy clusters, a strange and unexpected pattern began to emerge from the noise. The clusters were not moving randomly as one would expect in a universe that is homogeneous on large scales. Instead, a significant number of them, particularly those located in a vast swath of the sky centered on the Centaurus cluster, seemed to be moving in a coherent direction with a velocity that could not be explained by the gravitational pull of any of the known structures within the observable universe. It was as if a powerful unseen current was dragging them along a cosmic river flowing through the fabric of space-time. This was the birth of the dark flow hypothesis. The initial findings, which were published in 2008, were met with a mixture of intense excitement and considerable skepticism from the broader scientific community. The signal was statistically significant, but the measurements were incredibly difficult and pushed the limits of the available technology and analytical techniques. The term dark flow was coined to capture the mysterious nature of this movement, implying a connection to unseen or dark sources of gravity that lay beyond our direct view. Subsequent studies with the aim of either confirming or refuting these initial observations were immediately undertaken. Scientists looked for the same signal in other datasets, including the more precise and detailed measurements of the cosmic microwave background that were later provided by the European Space Agency's Planck satellite. The results of these follow-up studies were mixed and have been the subject of ongoing debate. Some analyses found hints of the flow, but at a lower level of statistical significance than the original claim. Other analyses found no evidence for a coherent flow at all. This ambiguity has fueled a lively and productive debate in the cosmological community. The central challenge lies in the difficulty of untangling the faint dark flow signal from a multitude of other much larger effects. Our own galaxy. The Milky Way is moving through space at a speed of over 600 kilometers per second relative to the cosmic microwave background. This motion and the motion of our local group of galaxies must be carefully and precisely accounted for and subtracted from the data before any larger-scale flow can be detected. The gravitational pull of nearby superclusters, such as the massive Shapley supercluster, also creates significant local flows that can mimic or mask a larger, more distant signal. The controversy has pushed scientists to develop new and more robust statistical methods and to design new observational strategies that can probe these large-scale motions with greater accuracy and with fewer systematic uncertainties. Despite the ongoing debate about its reality, the possibility of dark flow has had a profound and lasting impact on theoretical cosmology. It has forced physicists to take seriously the idea that our observable universe may not be the whole story. It has inspired new and more complex models of cosmic inflation, exploring scenarios in which the initial expansion of the universe was not perfectly uniform and may have left behind large-scale gradients or tilts that could drive a cosmic flow in the modern era. It has also given new life and a new sense of urgency to speculative ideas about the multiverse, providing a potential, though highly tentative, observational window into a reality that lies beyond our own. The story of dark flow is a perfect and beautiful illustration of the scientific process in action. An unexpected and anomalous observation leads to a bold and creative hypothesis, which is then subjected to rigorous testing, intense scrutiny, and vigorous debate. Whether dark flow ultimately proves to be a real and fundamental feature of our cosmos or a subtle and elusive illusion, the quest to understand it has already pushed the boundaries of our knowledge and has opened up new and exciting avenues of research into the deepest and most profound mysteries of the universe. To unravel this intricate cosmic puzzle, scientists employ a rich and diverse arsenal of observational techniques, each providing a unique and complementary piece of the puzzle. The analysis of the cosmic microwave background remains a cornerstone of this monumental effort. By mapping the temperature fluctuations of the cosmic microwave background with ever-increasing precision, as was done so spectacularly by the WMAP and Planck satellites, scientists can create a detailed and nuanced picture of the early universe. These maps serve as a fundamental backdrop against which the motion of all modern-day structures can be measured with absolute precision. The kinematic Sunyaev-Zeldovich effect is a powerful but technically demanding tool for this purpose. It requires not only a precise and accurate map of the cosmic microwave background, but also detailed X-ray observations of the galaxy clusters in question in order to determine the properties of the hot gas that they contain. By carefully combining these different datasets, astronomers can isolate the faint and subtle signal of the cluster's motion from the much larger signal of the primordial temperature fluctuations. In parallel with these detailed cosmic microwave background studies, astronomers rely on the vast amounts of redshift data that have been collected by massive galaxy surveys. Redshift is the phenomenon where the light from distant objects is stretched to longer, redder wavelengths as the objects move away from us due to the relentless expansion of the universe. The amount of redshift that is measured for a galaxy is a direct and precise measure of its recessional velocity. By measuring the redshifts of millions upon millions of galaxies, ambitious surveys like the Sloan Digital Sky Survey have created vast and detailed three-dimensional maps of the cosmos. Within these maps, scientists can identify the peculiar velocities of galaxies, their individual motions relative to the smooth overall expansion of the universe. These peculiar motions are caused by the gravitational pull of all the local structures in their cosmic neighborhood. By mapping these velocity fields over vast volumes of space, researchers can look for large-scale coherent flows that might extend beyond the influence of the known superclusters. This method is highly complementary to the cosmic microwave background technique. It directly measures the motion of the galaxies themselves rather than their subtle effect on the background radiation. Gravitational lensing provides another powerful, albeit indirect way to probe the distribution of mass in the universe. According to Einstein's theory of general relativity, the immense gravity of a massive object such as a galaxy cluster can bend the path of light that comes from more distant objects that are located behind it. This can distort the images of these background galaxies, creating beautiful and intricate arcs and rings of light. By carefully analyzing these distortions, astronomers can create a detailed map of the mass distribution in the foreground cluster, a map that includes both its visible matter and its much larger component of dark matter. By creating such mass maps for many different clusters, scientists can test whether the observed distribution of matter in the universe is sufficient to explain the observed motions of galaxies. If there is a persistent, unexplained motion that does not correlate with the mapped mass, it would provide strong and compelling evidence for a gravitational pull from beyond the regions that we can map with the technique of gravitational lensing. One of the landmark studies that brought the phenomenon of dark flow into the scientific spotlight was the careful analysis of a large catalog of several hundred galaxy clusters combining their detailed X-ray properties with the data from the WMAP satellite. This study found a coherent bulk flow on scales of hundreds of millions of light-years a scale that is far larger than that of any known supercluster in the universe. The direction of this flow towards a region of the sky located between the constellations of Centaurus and Vela was particularly tantalizing, as it pointed to a region of the sky that was relatively sparse in known massive structures. This hinted that the source of the gravitational pull might lie much farther away beyond the reach of our current galaxy surveys. To quantify the statistical significance of such a large-scale flow, scientists must rely on sophisticated and powerful computational methods. They use what are known as Monte Carlo simulations to generate thousands upon thousands of virtual universes based on the standard cosmological model. In these simulated universes, they can measure the expected magnitude of random large-scale flows that arise purely by chance from the random distribution of matter. By comparing the observed flow in the real universe to this distribution of random flows, they can calculate the probability that the observed signal is nothing more than a statistical fluke. The initial studies suggested that the probability of such a large coherent flow occurring by chance was less than 1%, lending significant weight to the idea that it was a real and physical phenomenon. The phenomenon of dark flow is conceptually distinct from the other great cosmic mysteries of dark matter and dark energy, yet it is deeply and inextricably intertwined with them. Dark matter, which accounts for about 27% of the total mass energy content of the universe, is a form of matter that interacts with the rest of the universe primarily and perhaps exclusively through the force of gravity. It does not emit, absorb, or reflect light, making it completely invisible to our telescopes. We are forced to infer its existence from its subtle but powerful gravitational effects on the visible matter that we can see the unexpectedly high rotation speeds of galaxies, the frenetic motions of galaxies within clusters, and the intricate and beautiful patterns of gravitational lensing that are observed around massive objects. Dark matter provides the invisible gravitational scaffolding upon which the entire large-scale structure of the universe is built. Dark energy, which makes up roughly 68% of the cosmos, is even more mysterious and enigmatic. It is a form of energy that seems to be inherent to the very fabric of space-time itself, and it has a repulsive gravitational effect, causing the expansion of the universe not to slow down as one might expect due to the gravitational pull of all the matter, but to accelerate at an ever-increasing rate. Now we must consider the phenomenon of dark flow. It is not a substance like dark matter, nor is it a fundamental property of space like dark energy. It is an observed motion, a collective drift of entire clusters of galaxies. The connection to the other dark components arises when we ask the fundamental question, what could be causing this motion? The most straightforward and conservative explanation is gravity. A coherent flow of galaxies implies a gravitational pull from a massive concentration of matter. Since the known distribution of both visible matter and dark matter within our observable universe does not seem to be sufficient to explain the observed flow, the hypothesis naturally arises that the source of this immense gravitational pull lies beyond our cosmic horizon. This would imply the existence of vast unseen structures, supercontinents of dark matter in the wider unobservable universe. In this sense, dark flow could be a probe, a gravitational messenger from a realm of the cosmos that is otherwise completely inaccessible to us. The relationship with dark energy is more subtle and speculative, but no less profound. The standard model of cosmology assumes that dark energy is perfectly uniform throughout all of space, a cosmological constant whose repulsive effect is the same everywhere and in every direction. However, some alternative and more exotic theories propose that dark energy might not be a constant at all. It could be a dynamic field one that can vary in space or in time, or it could have more complex and interesting properties. If dark energy were not perfectly uniform, it could potentially create large-scale variations in the expansion rate of the universe, which might manifest themselves as a bulk flow of galaxies. In this scenario, dark flow would not be caused by a gravitational pull from unseen matter, but rather by a cosmic push from an uneven distribution of dark energy. This would be a truly revolutionary discovery, as it would provide the first ever evidence that dark energy is more dynamic and complex than a simple cosmological constant. The existence of dark flow therefore poses a profound and direct challenge to our understanding of the cosmic inventory. It suggests that our current models, which are based entirely on observations that have been made from within our limited cosmic horizon, may be missing a crucial and fundamental piece of the puzzle. The universe may be less uniform, more structured, and more interconnected on the very vastest scales than we have previously imagined. The ongoing debate over dark flow highlights the deep and intricate interplay between these different cosmic mysteries. Unraveling the true nature of dark flow could provide crucial and invaluable clues about the distribution of dark matter on superhorizon scales. Conversely, a better and more complete understanding of the properties of dark energy might offer a completely new and unexpected explanation for the observed flow. The three dark components of the cosmos, dark matter, dark energy, and dark flow, are not separate and isolated problems, but are rather different facets of a single overarching and magnificent quest to understand the fundamental nature and the ultimate evolution of our universe. The term dark flow may conjure up images of a malevolent unknown cosmic force, but in reality it simply refers to a velocity, a collective and coherent movement of galaxy clusters that hints at the profound influence of unseen mass on cosmic scales. This movement is not consistent with the detailed predictions of the standard cosmological model, which is built upon the foundational assumption of an isotropic and homogeneous universe. This model posits that on the grandest of scales, the universe should appear to be the same in all directions. Dark flow, with its clear and preferred direction of motion, directly and powerfully challenges this foundational notion. It suggests that our cosmic neighborhood may be embedded within a larger tilted structure, a cosmic landscape with vast hills and deep valleys of gravitational potential that extend far beyond our current view. If this is indeed the case, then our models of the cosmos, which are built upon the data that we can gather from within our own observable bubble, may need to be fundamentally and radically revised. The implications for our understanding of the long and complex story of cosmic evolution are significant. The formation of the large-scale structures that we see in the universe today, such as the cosmic web of galaxies and voids, is thought to have been seeded by tiny quantum fluctuations that occurred in the very early universe. These fluctuations were then stretched to cosmic proportions by the process of inflation. The statistical properties of these primordial fluctuations are predicted to be almost perfectly uniform and isotropic. A large-scale flow like dark flow might indicate that the initial conditions of the universe were not as uniform as we have long thought, or that the process of inflation itself left behind a residual large-scale asymmetry. This would be a profound discovery, as it would provide a direct and unprecedented window into the physics of the first moments of creation. It would also force us to reconsider the very concept of our universe as a completely self-contained and isolated system. If the gravitational influence of structures that lie beyond our horizon can affect the dynamics of the structures that lie within it, then our cosmos is not isolated. It is an integral part of a larger interconnected metastructure. This idea inevitably leads to deep and far-reaching philosophical contemplations. If our universe is just one part of a much larger whole, what does that say about our place in the grand scheme of things? The Copernican principle, which has guided scientific thought for centuries, posits that we do not occupy a special or privileged position in the universe. The discovery of dark flow could be seen as a powerful and dramatic extension of this principle to an even grander and more mind-boggling scale. Not only is our planet not the center of the solar system and our galaxy not the center of the universe, but our entire observable universe may not be the center or even a representative sample of the totality of existence. It may be just a small and insignificant province in a vast unseen empire subject to the gravitational laws of a distant unknown and perhaps unknowable capital. In summary, while dark matter and dark energy are fundamental components of the very fabric of the universe, influencing its structure and its expansion from within, dark flow represents a potential and tantalizing connection to a reality that lies outside our direct perception. It is a hint that the story of our cosmos may be written on a far larger and more magnificent page than the one that we are currently able to read. The observation of a coherent and directed motion of galaxy clusters a cosmic current that seems to be flowing towards an unseen and mysterious destination is a finding that resonates with the deepest and most profound questions about the ultimate structure of our universe. It challenges the very idea of an isolated and self-contained cosmos, suggesting instead that we are part of a much larger interconnected system, one that is influenced by regions of space that we cannot directly see, and perhaps even by other universes if the multiverse hypothesis holds any truth. Such a revelation would not just be a minor refinement of our existing models of the cosmos. It would be a true paradigm shift, a fundamental and radical reordering of our cosmic map. It would force us to confront the inherent and perhaps insurmountable limitations of our perception, and to acknowledge that the universe that we inhabit might be profoundly and fundamentally different from the universe that we can observe. The implications for our understanding of the long and complex story of cosmic evolution are equally profound. The standard model of cosmology, with its elegant and compelling story of a hot, dense beginning followed by billions of years of expansion and cooling, is built upon the foundational assumption of large-scale uniformity and isotropy. Dark flow, if it is confirmed to be a real phenomenon, would introduce a new and powerful element into this grand narrative. It would suggest that the initial conditions of our universe were not perfectly smooth and uniform, or that gravitational forces from beyond our horizon have been actively shaping the evolution of the structures within it all along. This could lead to a fundamental reevaluation of our understanding of how galaxies and clusters of galaxies formed, how the intricate and beautiful cosmic web was woven, and how the delicate and dynamic balance between the attractive force of gravity and the repulsive force of dark energy has played out over the vast sweep of cosmic time. Moreover, the study of dark flow could provide a completely new and powerful tool for probing the fundamental laws of physics. If the observed motion is indeed caused by the force of gravity, then it is a test of Einstein's theory of general relativity on the largest possible scales that are far beyond anything that we can probe with any other method. Any deviation from the predictions of general relativity in the behavior of dark flow could signal the presence of new physics, a subtle modification of the law of gravity that only becomes apparent over vast interuniversal distances. This would be a discovery of monumental and historic importance, one that could potentially lead to a unified theory that finally reconciles the two great pillars of modern physics: the worlds of the very large and the very small, the disparate realms of cosmology and quantum mechanics. The quest to understand the phenomenon of dark flow is also a powerful and relentless driver of technological innovation. To either confirm or refute its existence, astronomers need to push the boundaries of observational technology to their absolute limits. They need more sensitive and powerful telescopes that are capable of detecting the faint, subtle signals of galactic motion across billions upon billions of light years. They need more powerful and sophisticated supercomputers to run simulations of ever greater complexity and fidelity. And they need more sophisticated and robust statistical techniques to extract the faint and elusive dark flow signal from the overwhelming and ever-present noise of the cosmos. This relentless pursuit of knowledge fuels a virtuous and self-perpetuating cycle of scientific and technological progress, with each new discovery and each new innovation enabling the next. In a broader and more philosophical sense, the mystery of dark flow touches upon some of the most fundamental and enduring questions that have preoccupied humanity for millennia. What is the true and ultimate extent of the universe? Are we alone in the cosmos, or are we part of a much larger and more ancient cosmic community? What is our place in this vast and perhaps infinite reality? While science may never be able to provide definitive and final answers to all of these profound questions, the exploration of phenomena like dark flow brings us ever closer to a deeper and more nuanced understanding of our cosmic context. It encourages a sense of profound wonder and deep humility, a recognition of the vastness of our ignorance in the face of the universe's boundless and breathtaking complexity. It reminds us that we are still in the very early and tentative stages of our cosmic journey, with countless new worlds of knowledge waiting to be discovered. The crucial role of observational evidence in the field of astronomy cannot possibly be overstated. It is the solid and unyielding bedrock upon which our entire understanding of the universe is built. Without the careful, patient, and meticulous collection and analysis of data that comes to us from the cosmos, all of our elegant and beautiful theories would be nothing more than abstract mathematical speculations untethered to the reality that they purport to describe. The long and storied history of astronomy is in essence a history of observation, a history of looking at the sky with ever more powerful and sophisticated tools, and with a relentless and insatiable curiosity. The discovery of the cosmic microwave background is a prime and powerful example of the transformative power of observation. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, detected a faint, persistent, and annoying background noise in their sensitive radio telescope, a gentle hiss that seemed to come from every direction in the sky with equal intensity. This, as it turned out, was the first direct evidence of the Big Bang, the faint residual heat from the creation of the universe itself. It was a discovery that transformed the field of cosmology from a branch of theoretical physics filled with speculation and debate into a precision observational science. Similarly, the observation of the redshift of distant galaxies by the astronomer Edwin Hubble in the 1920s was a true watershed moment in our understanding of the cosmos. By meticulously measuring the spectra of light from dozens of different galaxies, Hubble found that almost all of them were moving away from us, and that the farther away a galaxy was, the faster it was receding from us. This was the first direct and compelling evidence for the expansion of the universe, a discovery that fundamentally and irrevocably changed our perception of a static, eternal, and unchanging cosmos. These observations provided the firm empirical foundation for the Big Bang theory, and they raised profound and far-reaching questions about the origin, the evolution, and the ultimate fate of the universe. In more recent decades, the discovery of thousands upon thousands of planets that are orbiting other stars has opened up a new and exciting frontier of observational astronomy. Using a variety of clever and sensitive techniques, such as the transit method, where astronomers detect the slight and periodic dimming of a star's light as a planet passes in front of it, and the radial velocity method, which detects the slight and rhythmic wobble of a star that is caused by the gravitational pull of an orbiting planet, we have moved from merely speculating about the existence of other worlds to cataloging them by the thousands. The Kepler Space Telescope in particular has been a revolutionary and transformative instrument in this field, revealing that planets are a common and perhaps even ubiquitous feature of our galaxy. This wealth of observational evidence has ignited the scientific search for life beyond the confines of our own Earth, as we are now beginning to analyze the atmospheres of these distant and exotic worlds for the chemical signatures of biology. The first direct detection of gravitational waves in the year 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, was another spectacular triumph of observational science. These subtle and elusive ripples in the very fabric of spacetime, which are created by the collision of massive and compact objects like black holes and neutron stars, were predicted by Albert Einstein a full century earlier, but had never been directly observed. The detection of these waves opened up a completely new and revolutionary way of observing the universe, a way that is not dependent on light or any other form of electromagnetic radiation. Gravitational wave astronomy allows us to listen to the most violent and energetic events that occur in the cosmos, providing deep and profound insights into the nature of gravity, the properties of black holes, and the physics of matter under the most extreme conditions imaginable. All of these landmark and historic discoveries underscore the central and indispensable role of observation in advancing our knowledge of the universe. And it is in this long and noble tradition that the story of dark flow is situated. It is a phenomenon that emerged from the careful, meticulous, and painstaking observation of the motion of galaxy clusters, a subtle and unexpected anomaly in the data that hinted at the existence of a deeper, unseen, and perhaps unknowable reality. The initial tantalizing hint of this cosmic enigma came from the painstaking analysis of a vast amount of data that was collected by NASA's Wilkinson Microwave Anisotropy probe. The WMAP satellite spent nearly a full decade of its operational life meticulously mapping the faint afterglow of the Big Bang, the cosmic microwave background radiation. Within these detailed and beautiful maps of the infant universe, scientists found that the temperature of this ancient light was not perfectly and completely uniform. There were tiny and subtle fluctuations, hot and cold spots, that represented the seeds of all future cosmic structure. It was in the context of these primordial fluctuations that the motion of nearby and modern galaxy clusters was carefully and precisely studied. When astronomers compared the expected temperature of the cosmic microwave background in the direction of a given cluster with the actual measured temperature, they could detect a subtle and characteristic shift that was caused by the cluster's motion through space. This technique revealed something startling and unexpected. A large number of clusters, spanning a vast and contiguous region of the sky, were all moving together in a coherent and directed stream, a bulk flow that was not aligned with any of the known gravitational structures in their cosmic vicinity. This peculiar and unexplained motion suggested that these galaxy clusters were being pulled along by an unseen and powerful force, a gravitational influence from a source that was so massive and so distant that it lay beyond the reach of our most powerful telescopes. This hypothetical and unseen source was dubbed the Great Attractor, and the collective and coherent motion of the clusters was termed dark flow. The initial observations were tantalizing but also highly controversial. The signal that was detected was weak, and the analysis that was required to extract it from the data was incredibly complex and difficult, requiring the careful and precise subtraction of many known and larger effects, including the motion of our own galaxy through the cosmos. Further investigations using the more precise and detailed data that was later collected by the Planck satellite have yielded a more complex and nuanced picture of the situation. The evidence for a single large-scale dark flow has become less certain and more ambiguous, but the studies have revealed a more intricate and fascinating tapestry of cosmic flows that are occurring on a variety of different scales, driven by the complex and beautiful distribution of matter in the cosmic web. The ongoing debate over the existence and the ultimate nature of dark flow highlights the immense challenges and the profound excitement of modern cosmology. It is a field of science where new and more precise observations are constantly pushing the boundaries of our theoretical understanding. The evidence for dark flow is still being gathered, analyzed, and debated, but the very possibility of its existence has already had a profound and lasting impact on the field of cosmology. It has spurred the development of new and more sensitive observational techniques, more sophisticated and powerful simulations, and more creative and imaginative theoretical models. It has forced us to confront the inherent and perhaps unavoidable limitations of our knowledge and to consider the possibility that our universe is far more complex and interconnected than we have ever dared to imagine. The story of dark flow is a powerful and humbling reminder that the universe is full of surprises and that the greatest and most profound discoveries often begin with a small, subtle, and unexplained anomaly in the data. The cosmic microwave background is more than just a faint and ancient glow from the distant past. It is a fundamental and indispensable pillar of modern cosmology. It is the most perfect example of blackbody radiation that has ever been observed in nature, a thermal echo of a time when the entire universe was a hot, dense, and opaque plasma. As the universe expanded and cooled, this plasma eventually became transparent to light, releasing the photons that we now observe as the cosmic microwave background. The remarkable and striking uniformity of this radiation across the entire sky is a powerful and compelling confirmation of the cosmological principle. But it is the tiny and subtle fluctuations that are present within this uniformity, the anisotropies, that hold the key to understanding the structure and the evolution of the universe. These minute variations in temperature on the order of just 1 part in 100,000 were first imprinted upon the cosmos during the epoch of cosmic inflation, and they grew over the vast sweep of cosmic time through the process of gravitational instability to form the galaxies and the clusters of galaxies that we see in the universe today. The connection between these ancient and primordial fluctuations and the modern and mysterious phenomenon of dark flow is a subtle but potentially profound one. The cosmic microwave background provides a universal and absolute rest frame, a background against which all motion in the universe can be measured with precision. When we observe the motion of a galaxy cluster, we are measuring its velocity relative to this cosmic microwave background rest frame. The expected motion of a cluster should be determined by the gravitational pull of all the matter in its cosmic vicinity, a distribution of matter that is traced by the distribution of other galaxies and, more fundamentally, by the anisotropies that are present in the cosmic microwave background itself. The dark flow anomaly arises when the observed motion of a cluster or a large group of clusters deviates significantly from this expected motion. It implies a gravitational pull from a source that is not accounted for in our maps of the matter distribution that lies within the observable universe. The incredibly detailed and precise measurements that were made by the WMAP and Planck satellites have provided us with exquisitely detailed maps of the cosmic microwave background anisotropies. These maps have allowed cosmologists to precisely and accurately determine the key parameters of our universe, such as its age, its geometry, and its composition of dark matter and dark energy. Within these maps, there are certain large-scale features that have drawn particular and intense attention in the context of the dark flow mystery. One such feature is the so-called cold spot, a large and unusually cold region in the cosmic microwave background sky. This cold spot is statistically highly unlikely to be a simple random fluctuation, and its ultimate origin is still a profound and unsolved mystery. One speculative but intriguing hypothesis is that the cold spot could be the gravitational signature of a vast supervoid, an enormous and ancient region of space with an unusually low density of both matter and dark matter. Another more exotic and even more speculative possibility is that it could be the result of a direct and ancient interaction between our own universe and another parallel universe. The tantalizing connection to the phenomenon of dark flow is that the direction of the observed bulk motion of some of the galaxy clusters seems to point towards this very same region of the sky. This has led to intense speculation that the cold spot and the dark flow could be related phenomena, both pointing to the existence of a massive unseen structure or a novel and unknown physical effect. The cosmic microwave background measurements also allow for a more subtle and nuanced test of the dark flow hypothesis. The gravitational potential of large-scale structures in the universe can affect the path of the cosmic microwave background photons as they travel towards us through a phenomenon that is known as the integrated Sachs-Wolf effect. This effect causes additional and characteristic temperature fluctuations in the cosmic microwave background that are correlated with the distribution of matter in the late universe. If there is a massive unseen structure that is driving the dark flow, it should also leave a subtle and detectable imprint on the cosmic microwave background through this effect. Searches for such a correlation have been conducted, but the results have so far been inconclusive, limited by the faintness of the signal and the inherent complexities of the analysis. The intricate and deep relationship between the cosmic microwave background and the phenomenon of dark flow underscores the profound interconnectedness of all cosmic phenomena. The oldest light in the universe holds within it crucial clues about the largest and most mysterious motions that are occurring in the modern cosmos. Unraveling this deep and fundamental connection is one of the great and ongoing challenges of modern cosmology, a challenge that requires a deep and nuanced understanding of both the early universe and the complex and beautiful dynamics of the cosmic web. Galaxy clusters, the most massive gravitationally bound objects in the known universe, are the primary and most powerful tracers of the phenomenon of dark flow. These cosmic behemoths, which can contain hundreds or even thousands of individual galaxies, along with vast and diffuse amounts of hot gas and dark matter, serve as ideal and natural laboratories for studying the large-scale dynamics of the cosmos. Their immense and concentrated mass makes them incredibly sensitive probes of the underlying gravitational field that permeates the universe, and their brightness, in both the optical and the X-ray wavelengths of the electromagnetic spectrum, makes them detectable out to vast and cosmological distances. When astronomers carefully and precisely study the motion of these massive clusters, they are not just measuring the speed of individual galaxies, but the collective and coherent movement of an entire cosmic metropolis. The peculiar velocity of a galaxy cluster is a delicate and difficult signal to extract from the observational data. It must be carefully and precisely distinguished from the much larger and more dominant Hubble flow, the recession velocity, that is due to the relentless expansion of the universe. This is done by comparing the cluster's measured redshift with the redshift that would be expected for an object that is located at its distance from us. The small difference between these two values gives the peculiar velocity the motion of the cluster through space independent of the cosmic expansion. The profound intrigue of dark flow arises from the observation that the peculiar velocities of many different clusters scattered across a vast and contiguous volume of space are not random in their direction. Instead, they exhibit a coherent directed motion, a bulk flow that suggests that they are all responding to a common large-scale gravitational influence. This is a phenomenon that is not expected in the standard cosmological model, which predicts that the peculiar velocities of objects should be largely random on scales that are larger than a few 100 million light-years. The existence of such a large and coherent flow implies a source of gravity that is both incredibly massive and incredibly distant, a structure that lies far beyond the scale of the known superclusters that are located in our cosmic neighborhood. The analysis of these cluster motions is a multifaceted and complex scientific endeavor. It requires not only precise and accurate measurements of their redshifts, but also accurate and reliable determinations of their distances from us. The measurement of cosmic distances is a notoriously difficult and challenging task, one that relies on a variety of different techniques, such as the use of what are known as standard candles, like Type Ia supernovae, or the detailed analysis of the intrinsic properties of the clusters themselves. Furthermore, these galaxy clusters are not just passive tracers of the cosmic flow, they are active and dynamic participants in the cosmic web. They are typically located at the nodes of this vast and intricate network of filaments and voids, the points where the great streams of intergalactic matter converge. The study of their motion provides deep and profound insights into the dynamics of this cosmic web, revealing how matter flows along the filaments and accretes onto the clusters over the course of cosmic time. The dark flow phenomenon suggests that this web itself may be in motion, that the entire large-scale structure in our local cosmic vicinity is being pulled along by a cosmic current that originates from a region that lies beyond our observational horizon. The gravitational lensing effect that is produced by these massive clusters provides another powerful and independent tool for studying the underlying mass distribution of the universe. By carefully mapping the dark matter halos of these clusters, astronomers can test whether the observed motions of the clusters are consistent with the gravitational pull of the matter that we can detect through its lensing effect. Any significant discrepancy between the observed flow and the gravitational field that is inferred from the lensing data would strengthen the case for an external, unseen, and perhaps unknowable influence. The ongoing search for dark flow is a scientific quest that is pushing the boundaries of observational cosmology to their absolute limits. It requires ever larger and more comprehensive surveys that are capable of mapping the positions and the motions of tens of thousands of galaxy clusters over the entire sky. It demands new and more accurate methods for measuring cosmic distances, and it calls for more sophisticated and powerful theoretical models and simulations to interpret the complex and beautiful patterns of cosmic flow. The study of galaxy clusters in relation to dark flow is a journey into the very heart of the cosmic web, a journey that is revealing the intricate and dynamic dance of matter on the grandest of scales and hinting at a universe that is far more mysterious and interconnected than we have ever dared to imagine. The distribution of galaxies across the vast expanse of the cosmos is not a random and chaotic scattering of matter, but a complex, structured, and beautiful tapestry, the cosmic web. This intricate and delicate web, with its dense and luminous filaments, its massive and ancient clusters, and its vast, dark, and empty voids, is the result of the relentless and patient work of gravity over the course of 13.8 billion years, pulling matter together from the nearly uniform and featureless soup of the early universe. The task of mapping this colossal structure is a monumental one, a cosmic cartography that has been undertaken by a series of ambitious and large-scale projects such as the Sloan Digital Sky Survey. By collecting the light from millions upon millions of individual galaxies, these surveys have created a detailed and breathtaking three-dimensional map of our cosmic neighborhood, a map that reveals the intricate and awe-inspiring architecture of the universe on the very largest of scales. This map is not a static and unchanging one. It is a dynamic, evolving system, and by carefully and precisely studying the motions of the galaxies that are contained within it, we can learn about the fundamental forces that shape its long and complex evolution. The investigation of the phenomenon of dark flow is in essence a search for anomalies within this grand cosmic map, a search for coherent and large-scale motions that deviate from the expected behavior of the universe. The Hubble flow. The overall and uniform expansion of the universe is the dominant and most obvious motion on large scales. But superimposed on top of this are the peculiar velocities of individual galaxies, their individual and unique movements that are caused by the gravitational pull of all the nearby structures. A galaxy that is located on the edge of a massive cluster will be pulled inexorably towards it, while a galaxy that is located near a large and empty void will be gently pushed away from it. By meticulously measuring these peculiar velocities for a large and representative number of galaxies, astronomers can create what is known as a velocity field map, a detailed and nuanced picture of the gravitational landscape of the universe. The dark flow hypothesis posits that on the very largest of scales, this velocity field is not random, but exhibits a coherent directed flow, a bulk motion that cannot be explained by the gravitational pull of the structures that are contained within the map itself. The process of detecting such a large-scale flow is a delicate and difficult statistical exercise. It involves measuring the velocities of thousands upon thousands of galaxies relative to the cosmic microwave background, which acts as a fixed and absolute reference frame for the entire universe. These precise measurements are then compared to the detailed predictions of the standard cosmological model, a model that is based on the observed distribution of matter in the cosmos. Any statistically significant deviation between the observed and the predicted velocity fields could be a sign of the existence of dark flow. One of the key and most influential studies in this field focused on the motion of galaxies in the vicinity of the cosmic microwave background using a sophisticated technique that combines the redshift data from galaxies with other independent distance indicators. This study found compelling evidence for a bulk flow that extends out to a distance of several 100 million light-years a scale, at which the universe is expected to be largely and almost perfectly homogeneous. The direction of this flow towards the constellation of Centaurus was consistent with the earlier and independent findings that had come from the studies of galaxy clusters. These findings have sparked a vigorous and ongoing debate within the scientific community. The signal that has been detected is subtle and faint, and the analysis that is required to extract it from the data is fraught with a multitude of potential systematic errors. The calibration of cosmic distances is a major and persistent source of uncertainty in cosmology, and any small and seemingly insignificant error in the distance scale can translate into a large and significant error in the inferred peculiar velocity of a galaxy. Furthermore, the limited and incomplete sky coverage of some of the earlier surveys can introduce subtle biases that might mimic a coherent and large-scale flow. The scientific community is actively and diligently working to address these immense challenges, developing new and more powerful observational techniques and more robust and reliable statistical methods. The analysis of the cosmic web provides another and deeper layer of insight into this mystery. The filaments of this web are the great superhighways of the universe, the channels along which matter flows from the great voids to the massive clusters. The motion of galaxies along these filaments is a natural and expected consequence of the process of gravitational instability. The fundamental question is whether these filamentary flows are sufficient to explain the observed large-scale motions, or whether an additional external and perhaps unknown influence is required. The answer to this profound and far-reaching question lies in the future, in the vast amounts of data that will be collected by the next generation of galaxy surveys. Surveys that will map the universe with an unprecedented and breathtaking depth and precision, providing the definitive and final test of the dark flow hypothesis. The quest to unravel the deepest mysteries of the universe is a journey of both meticulous observation and bold imagination. a delicate and intricate dance between the data that we gather from the cosmos and the theoretical frameworks that we construct in order to make sense of it. The primary tools in this monumental endeavor are the great observatories of the world, the technological marvels that act as our extended and powerful senses, allowing us to peer into the unfathomable depths of space and time. The study of the cosmic microwave background, the fossil light that has been traveling to us from the time of the Big Bang, has been revolutionized by a series of ambitious and successful space-based missions. NASA's Cosmic Background Explorer, or COBE, provided the very first and groundbreaking evidence for the existence of tiny and subtle temperature fluctuations in the cosmic microwave background. The Wilkinson Microwave Anisotropy Probe, or WMAP, then went on to map these fluctuations with much greater and more revealing detail, ushering in the modern era of precision cosmology. And the European Space Agency's Planck satellite has given us the most detailed and beautiful picture of the infant universe to date, its data providing the most stringent and powerful tests of our current cosmological models. These incredible and sophisticated instruments, by measuring the faint and ancient glow of the early universe, have become our most powerful probes of cosmic origins and evolution, and they are absolutely central to the ongoing investigation of the phenomenon of dark flow. In parallel with these detailed cosmic microwave background observatories, a new and more powerful generation of ground-based and space-based telescopes is currently mapping the large-scale structure of the universe in unprecedented and breathtaking detail. The Sloan Digital Sky Survey has been a true workhorse in this field for more than 2 decades, creating a vast and invaluable digital atlas of the cosmos. Its remarkable legacy is now being carried forward by new and even more ambitious projects such as the Dark Energy Survey and the Legacy Survey of Space and Time, which will be conducted at the magnificent Vera C. Rubin Observatory in the high mountains of Chile. These surveys are specifically designed to map billions upon billions of galaxies, tracing the cosmic web with an exquisite and unparalleled precision. Their vast and rich data will allow for the most accurate and reliable measurements of the peculiar velocities of galaxies and clusters that have ever been made, providing a definitive and final test of the dark flow hypothesis. The clarity and sharpness of the images that are produced by these ground-based telescopes are greatly enhanced by the use of what are known as adaptive optics systems, which are used in world-class facilities like the Keck Observatory in Hawaii. These sophisticated systems use deformable and computer-controlled mirrors to correct for the blurring and distorting effects of the Earth's turbulent atmosphere, achieving a level of sharpness that can rival that of the telescopes that are located in space. Radio telescopes provide another and unique window into the cosmos. The Atacama Large Millimeter Submillimeter Array, or ALMA, which is located in the high desert of Chile, is an incredibly powerful and sensitive instrument for studying the cold gas and dust that is present in galaxies, the raw and fundamental material for the formation of new stars. By carefully observing the motion of this gas, astronomers can probe the gravitational dynamics of galaxies and their intricate and complex interaction with the surrounding and diffuse intergalactic medium. The upcoming Square Kilometer Array, an ambitious and monumental international project to build the world's largest and most sensitive radio telescope, will completely revolutionize this field of study, providing the ability to map the distribution of hydrogen gas throughout the entire history of the cosmos. In the realm of theoretical work, supercomputer simulations are an absolutely indispensable tool. These simulations, which can model the evolution of billions of individual particles over the entire sweep of cosmic time, are our virtual laboratories for exploring the universe. They allow us to test our most fundamental theories of dark matter, dark energy, and galaxy formation against the hard and unforgiving data that comes from our observations. By creating simulated universes with and without a dark flow, researchers can determine the unique and characteristic observational signatures of such a phenomenon, guiding the search for it in the real and physical universe. The intricate and dynamic interplay between these advanced and powerful instruments, these sophisticated and complex simulations, and these bold and imaginative theoretical ideas is the very engine of progress in the field of cosmology. It is a collaborative, international, and deeply human effort, a testament to our collective and enduring desire to understand our place in the cosmos. Theoretical frameworks are the intellectual scaffolding upon which our entire understanding of the universe is built. They are the grand and overarching narratives that weave together a multitude of disparate and seemingly disconnected observations into a coherent and beautiful picture of reality. Einstein's general theory of relativity is one such framework, a revolutionary and profound reconceptualization of the force of gravity as the intrinsic curvature of spacetime. It has been a spectacularly and enduringly successful theory. Its predictions confirmed time and time again by countless observations from the subtle bending of starlight by the sun to the recent and dramatic detection of gravitational waves from the cataclysmic merger of two black holes. The Standard Model of particle physics is another such framework, a remarkably precise and comprehensive description of the fundamental particles and forces that make up the known non-gravitational world. The triumph of this model was capped by the historic discovery of the Higgs boson at the CERN laboratory in 2012, the particle that is responsible for giving mass to all the other fundamental particles. Yet despite their incredible and undeniable successes, these frameworks are known to be incomplete. General relativity does not incorporate the strange and counterintuitive rules of quantum mechanics, and the Standard Model does not include the force of gravity, nor does it provide any explanation for the existence of the mysterious dark matter and dark energy that dominate the cosmos. In the field of cosmology, the Big Bang theory, augmented by the powerful and elegant concept of cosmic inflation, provides the dominant and most successful framework for understanding the origin and the evolution of the universe. It is a powerful and compelling theory, one that is supported by a wealth of different lines of evidence, from the observed expansion of the universe and the properties of the cosmic microwave background radiation to the observed abundances of the light elements that were forged in the first few minutes of the universe's existence. However, it is also a framework that is filled with unanswered questions and unresolved tensions. The ultimate nature of the initial singularity, the precise physical mechanism that drove the process of inflation, and the origin of the observed asymmetry between matter and antimatter in the universe are all deep and profound mysteries. Astrobiology. The scientific study of the potential for life beyond the Earth also relies on theoretical frameworks to guide its search. The famous Drake equation, though it is more of a probabilistic argument than a true physical theory, provides a useful and insightful way of organizing the various factors that might determine the number of intelligent communicative civilizations that are present in our Milky Way galaxy. It highlights the vastness of our ignorance and the immense and daunting challenge of the search for extraterrestrial intelligence. In the quest to move beyond these established and well-tested frameworks, physicists have developed more speculative and more ambitious theoretical ideas. String theory is one such idea, a leading candidate for a quantum theory of gravity that proposes that the fundamental constituents of the universe are not point-like particles, but are instead tiny one-dimensional vibrating strings. It is a theory of incredible mathematical elegance and power, and it naturally and beautifully predicts the existence of extraspatial dimensions. However, it has yet to make a single definitive and testable prediction that would allow it to be either confirmed or refuted by experiment. The great mystery of dark flow sits at the very intersection of these various theoretical frameworks. It is a phenomenon that directly challenges the standard cosmological model and may require a new and revolutionary theoretical understanding in order to explain it. One prominent theory, as we have explored, is that dark flow is the result of the gravitational effects of vast and unseen structures that lie beyond the boundaries of the observable universe. This idea is consistent with the predictions of some of the more exotic inflationary models, which suggest that our observable universe is just a small and perhaps insignificant patch of a much larger and potentially highly inhomogeneous meta-universe. Another more radical theory suggests that dark flow might be a direct manifestation of a subtle modification of the law of gravity on the very largest of scales. Perhaps Einstein's theory of general relativity is not the final and complete word on the nature of gravity, and on cosmic scales, a new long-range force comes into play. This would be a truly profound discovery, as it would require a fundamental and radical rethinking of our understanding of the nature of space-time. A third line of speculation connects the phenomenon of dark flow to the nature of dark energy. If dark energy is not a simple and unchanging cosmological constant, but is instead a dynamic and evolving field that can vary in space, then it could create large-scale gradients in the expansion of the universe that would drive a cosmic flow of matter. This would provide a powerful and new probe of the nature of dark energy, one that is complementary to the traditional methods of measuring the expansion history of the universe. These are just some of the theoretical ideas that have been proposed to explain the phenomenon of dark flow. Each of them is highly speculative, and each comes with its own set of unique challenges and profound implications. But the very existence of such a rich and diverse theoretical landscape is a testament to the power of a single unexplained observation to stimulate scientific creativity and to push the boundaries of human knowledge. The quest to understand dark flow is a journey into the very heart of theoretical physics. A search for a new story, a new framework that can encompass this and all the other great mysteries of the cosmos. The concept of cosmic inflation is a cornerstone of modern cosmology, a theoretical idea of breathtaking scope and immense power. Proposed in the early 1980s by physicists Alan Guth and André Linde, it posits that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. This hyper-expansion would have taken a region of space that was smaller than a single proton and stretched it to a size that was larger than the entire observable universe that we see today. This incredible and violent event, though it was unimaginably brief, would have had profound and lasting consequences, explaining several key and otherwise mysterious features of our cosmos. It explains why the universe is so remarkably flat and so strikingly uniform on the very largest of scales, and it provides a natural and elegant mechanism for generating the tiny primordial density fluctuations that were the seeds for the formation of all the cosmic structure that we see around us today. Inflation, in its essence, is the theory that explains how our universe got its initial conditions. The relationship between this ancient, formative, and violent event and the modern and mysterious phenomenon of dark flow is a subtle but potentially deep and profound one. One intriguing hypothesis is that dark flow could be a direct and observable remnant of the inflationary epoch itself. If the process of inflation was not perfectly and completely uniform, if it ended at slightly different times in different places across the nascent cosmos, or if the energy field that drove the process of inflation had large-scale and long-wavelength fluctuations, it could have imprinted a large-scale asymmetry, a tilt, onto the very fabric of the universe. This primordial tilt would manifest itself today as a large-scale gradient in the gravitational potential of the universe, a cosmic slope that would cause all the matter in our cosmic neighborhood to flow downhill. In this scenario, dark flow would be a true fossil, a direct and unprecedented observational window into the physics of inflation, a phenomenon that occurred when the universe was just a trillionth of a trillionth of a trillionth of a second old. This idea is both incredibly exciting and highly speculative. The standard and simplest models of inflation predict a very high degree of uniformity and isotropy, and any significant deviation from this prediction would require a more complex and perhaps less elegant model of the early universe. However, the potential payoff of such a discovery would be immense. If we could confirm that dark flow is indeed a remnant of the process of inflation, it would provide an unprecedented and unique probe of the physics of the very early universe, a realm of energies that are far beyond anything that we can ever hope to access in our terrestrial particle accelerators. The apparent tension between the predictions of the standard inflationary models and the tentative observations of dark flow has spurred the development of new and more creative theoretical models. Some cosmologists are now exploring scenarios in which multiple different inflationary fields were at play in the early universe, or in which the universe underwent multiple distinct phases of inflation. Others are considering the even more exotic and mind-bending possibility that our universe is just one single bubble in a vast, eternally inflating multiverse. In this picture, our bubble universe could have collided with another bubble in the distant and primordial past, an event of unimaginable violence that would have left a large-scale anisotropic imprint on our cosmos, a cosmic bruise that could be the ultimate source of the dark flow that we observe today. In essence, the relationship between the process of cosmic inflation and the phenomenon of dark flow is a part of the larger and more magnificent tapestry of cosmic evolution. The faint echoes of the universe's infancy may still be resonating through its vastness, shaping the grandest cosmic structures and the most mysterious cosmic motions. Understanding how these two seemingly disparate concepts interconnect is not just a matter of piecing together the long and complex history of our universe. It is a quest to understand the fundamental laws of physics that governed its creation, the ultimate nature of space-time itself, and the ultimate origin of everything that we see around us. It is a journey that takes us back to the very edge of time, to a moment of unimaginable energy and breathtaking creativity, a moment whose profound consequences are still unfolding today in the silent, mysterious, and beautiful flow of galaxies across the cosmic sea. The enigmatic and coherent motion of dark flow, this collective drift of entire galaxy clusters across the cosmic canvas, raises a fundamental and profound question. Can this strange phenomenon be explained within the established and well-tested frameworks of gravity? Or does it signal the urgent need for a new and revolutionary physics? The gravitational theories of Isaac Newton and Albert Einstein have been spectacularly and enduringly successful in describing the motions of celestial bodies, from the simple fall of an apple to the intricate orbit of a distant planet, from the fiery formation of a single star to the complex and beautiful dynamics of an entire galaxy. According to these well-established theories, the motion of a galaxy cluster should be determined entirely by the gravitational pull of all the matter in its cosmic vicinity, including both the visible matter that we can see and the much larger component of dark matter that we cannot. The dark flow anomaly arises because the observed motion seems to be larger and more coherent on large scales than can be accounted for by the known and mapped mass distribution in our local cosmic neighborhood. One possibility, perhaps the most conservative one, is that our maps of the mass distribution of the universe are simply incomplete. Perhaps there are vast, unseen structures of dark matter lurking just beyond the reach of our current surveys, whose immense gravitational pull is responsible for the observed flow. This would be a fascinating and important discovery, as it would imply that the cosmic web is even more structured and massive on the very largest of scales than our current models suggest. It would not, however, require a new and revolutionary theory of gravity. It would simply mean that our universe is more clumpy and inhomogeneous on the largest scales than we have previously thought. Another more radical possibility is that our understanding of the force of gravity itself is incomplete. General relativity has been tested with incredible and breathtaking precision in the relatively strong gravitational fields of the solar system and in the extreme environment of binary pulsar systems, but it has not been tested as rigorously on the very largest cosmological scales. It is conceivable that on scales of billions upon billions of light-years, the force of gravity behaves differently than Einstein's elegant theory predicts. Some theoretical physicists have proposed various modifications to the theory of general relativity theories that introduce new fields or new dimensions of space-time, which could lead to a long-range force that would be responsible for the phenomenon of dark flow. This would be a truly revolutionary and paradigm-shifting discovery, a profound and fundamental rethinking of our understanding of one of the four fundamental forces of nature. However, before we resort to such radical and speculative explanations, we must rigorously and exhaustively exhaust all other more mundane possibilities. The measurements of dark flow are incredibly challenging and are subject to a host of potential systematic errors. It is entirely possible that the observed signal is not a real physical phenomenon, but is instead the result of subtle, unaccounted-for biases in the data analysis. The calibration of cosmic distances, the precise modeling of our own motion through the universe, and the subtle effects of foreground contamination on the cosmic microwave background measurements are all potential sources of error that could mimic a dark flow signal. The scientific community is currently engaged in a rigorous and ongoing process of cross-checking the results that have been obtained from different observational techniques and from different research groups in order to either confirm the reality of the signal or to identify the ultimate source of the error. In summary, the mystery of dark flow presents us with a tantalizing and profound choice. It could be a sign that our universe is grander and more structured than we can currently see, a hint of unseen continents of matter that lie just beyond our cosmic horizon. It could be a faint whisper of a new and unknown law of physics, a subtle crack in the magnificent and beautiful edifice of Einstein's theory of gravity. Or it could be a ghost in the machine, a subtle and elusive artifact of our complex and imperfect methods of observing the cosmos. The quest to distinguish between these fascinating and profound possibilities is what drives the scientific enterprise forward, a relentless and unending pursuit of a deeper and more complete understanding of the vast and beautiful expanse of the universe. The large-scale structure of the universe. The cosmic web is the grand and magnificent stage upon which the cosmic drama of dark flow unfolds. This intricate and delicate network of luminous filaments, massive and ancient clusters, and vast, dark and empty voids is the physical and visible manifestation of the underlying density fluctuations that were present in the very early universe fluctuations that were amplified by the relentless and patient work of gravity over the course of 13.8 billion years. It is the fundamental framework that governs the motion of all the galaxies in the universe, channeling them along the great filaments into the dense and crowded nodes of the clusters. A deep and complete understanding of this colossal structure is absolutely essential for interpreting the phenomenon of dark flow, as it provides the crucial context, the gravitational landscape through which the great cosmic currents flow. The detailed and beautiful observations that have been made by the Great Galaxy Surveys have revealed the stunning and breathtaking complexity of this cosmic web. Galaxies are not distributed uniformly throughout space, but are instead arranged in a complex and hierarchical pattern, from small and intimate groups to massive and sprawling clusters, all of which are interconnected by vast, tenuous, and almost invisible bridges of matter. The phenomenon of dark flow appears to be a motion that is superimposed on top of the intricate and complex dynamics of this web. It is a bulk flow that seems to be largely independent of the local gravitational pulls of the individual filaments and clusters. This strongly suggests that its ultimate source, if it is indeed gravitational in nature, must be a structure that is even larger and more massive than the largest known superclusters in the universe. It could be a vast, unseen, and perhaps unknowable concentration of dark matter, a hypercluster that is pulling on our entire local cosmic neighborhood. By carefully and precisely examining the large-scale structure of the universe, scientists can model the expected gravitational field and predict the peculiar velocities of galaxies with a high degree of accuracy. The dark flow signal is the residual motion that remains after the gravitational influence of all the known and mapped structures has been carefully and precisely subtracted. The larger and more accurate our maps of the cosmic web become, the more precisely we can model this expected velocity field, and the more robustly we can test for the presence of a residual anomalous and unexplained flow. The sophisticated and powerful simulations of cosmic structure formation are a crucial and indispensable tool in this monumental endeavor. By creating vast and detailed virtual universes that evolve according to the known laws of physics, scientists can study the formation and the dynamics of the cosmic web in exquisite and unprecedented detail. They can investigate the magnitude of the random large-scale flows that are expected to arise naturally and by pure chance from the random alignment of structures in the standard cosmological model. This allows them to rigorously assess the statistical significance of the observed dark flow. If the observed flow is much larger than anything that is ever seen in the simulations, it would be strong and compelling evidence for the existence of new and unknown physics. The intricate and deep interplay between the large-scale structure of the universe and the phenomenon of dark flow is a rich and complex field of scientific study. It is a quest to understand the deepest and most fundamental properties of our universe, its structure, its dynamics, and its ultimate origins. The tools of modern cosmology, the advanced and powerful simulations, and the great and magnificent observatories are our means of engaging in a deep and meaningful dialogue with the universe. The simulations are our way of asking pointed and specific questions, of rigorously testing our hypotheses about the nature of dark matter, dark energy, and the fundamental laws of gravity. By creating these vast and detailed virtual cosmoses, we can explore the full and complex consequences of our theories, predicting the intricate patterns and the beautiful structures that should emerge from a given set of initial conditions and physical laws. We can observe how galaxy clusters form and interact with each other, how the intricate and delicate cosmic web is woven over the course of billions of years, and how the expansion of the universe evolves over the vast sweep of cosmic time. These simulations have become incredibly sophisticated and powerful, incorporating not just the subtle and powerful effects of gravity, but also the complex and messy physics of gas dynamic star formation and the powerful feedback from supernovae and active galactic nuclei. They allow us to create realistic, detailed, and beautiful models of the universe that can be directly and rigorously compared with our observations. The observations, in turn, are the universe's answers to our carefully posed questions. They are the vast amounts of data that are collected by our telescopes, the precious light from distant and ancient galaxies, the faint and primordial glow of the cosmic microwave background. By carefully and precisely comparing the results of our simulations with this real and unforgiving observational data, we can either validate or refute our most cherished theories. This intricate and dynamic back and forth between simulation and observation is the very engine of scientific progress. In the context of the mystery of dark flow, simulations are particularly and crucially important. They allow us to quantify the expected level of large-scale motion in the standard cosmological model. If the observed dark flow is significantly and consistently larger than the flows that are seen in the simulations, it would be a powerful and compelling indication that our standard model is incomplete. Furthermore, simulations allow us to test a variety of alternative and more exotic hypotheses about the ultimate nature of dark flow. We can create simulations in which the universe has a large-scale and primordial tilt in which the law of gravity is subtly modified on the very largest of scales, or in which there are massive and unseen structures that lie just beyond the observable horizon. And we can see if these alternative models can successfully reproduce the observed flow. These computer-generated models have also become powerful and invaluable tools for visualization and communication, making the complex and abstract concepts of cosmology more accessible and understandable to both the scientific community and the general public. They can demonstrate how the subtle and delicate interplay of gravity and dark energy shapes the cosmic web, and how even small and seemingly insignificant variations in the initial conditions of the universe can lead to vastly different and unpredictable outcomes. In essence, simulations serve as a vital and indispensable bridge between theory and observation, a framework through which we can explore the unseen and perhaps unknowable aspects of the cosmos and test the very boundaries of our current understanding of physics. As our technology and our computational power continue to advance at an exponential rate, these simulations will become ever more realistic and ever more powerful, providing deeper and more profound insights into the mysteries of dark flow and all the other great and enduring enigmas of the cosmos. The profound implications of cosmology are not confined to the esoteric and abstract realm of theoretical physics. They touch upon the deepest and most fundamental questions of our very existence. The discovery that our universe had a definite and specific beginning, the Big Bang, has fundamentally and irrevocably reshaped our understanding of time and the nature of creation. The stunning realization that the universe is not static and unchanging, but is instead expanding, and that this expansion is currently accelerating, has forced us to confront a future of increasing cosmic isolation and an eventual cold, dark, and empty end. The humbling and profound discovery that the ordinary matter that makes up our own bodies, our beautiful planet, and all the brilliant stars in the sky accounts for a mere 5% of the total cosmic inventory, with the rest being made up of the mysterious and unseen dark matter and dark energy, is a profound and powerful statement of our collective and deep-seated ignorance. It is a humbling and important reminder that we are only just beginning to scratch the surface of the true nature of reality. The detailed and beautiful study of the cosmic microwave background has given us a baby picture of the universe, revealing the tiny and primordial seeds of all future structure. The remarkable and striking uniformity of this ancient radiation, with its tiny, almost imperceptible fluctuations, has provided powerful and compelling evidence for the theory of cosmic inflation, a theory that suggests a period of hyper-rapid and violent expansion in the first moments of the universe's existence. The implications of cosmology also extend to the profound and ancient question of our place in the universe. The discovery of thousands upon thousands of exoplanets has shown us that planetary systems are a common and perhaps even ubiquitous feature of our galaxy, and that many of them may harbor worlds that are similar to our own. This has reignited the ancient and enduring question of whether we are alone in the universe, a question that has profound and far-reaching philosophical and existential implications. The various theories of the ultimate fate of the universe, the Big Chill, the Big Rip, or the Big Crunch, are not just abstract and dry physical scenarios. They are grand and sweeping narratives about the ultimate destiny of everything that we know and value. They force us to confront the finitude of our own existence on a truly cosmic scale. The great mystery of dark flow in this broader and more profound context is another and important thread in this grand and magnificent tapestry of cosmic inquiry. It challenges our most basic assumptions about the uniformity and the isolation of our universe. If dark flow is real, it implies that our cosmic home is not a self-contained island universe, but is instead an integral part of a larger interconnected system subject to influences from beyond our current observational horizon. This notion invites us to reconsider the very boundaries of our knowledge and the ultimate nature of reality itself. It could be a tantalizing hint that the universe is far larger, stranger, and more complex than we have ever dared to imagine. The ongoing research into this fascinating and enigmatic phenomenon is not just a quest for a new and more complete physical theory. It is a fundamental part of our collective human journey to understand our cosmic origins, our present reality, and our ultimate and perhaps unknowable fate. The observed motion of galaxy clusters, this coherent and directed drift towards the mysterious cold spot in the cosmic microwave background, is a phenomenon that directly and powerfully challenges our most basic models of cosmological expansion. The standard model of cosmology is built upon the foundational assumption that the expansion of the universe is isotropic, that is the same in all directions. Dark flow, with its clear and preferred direction, suggests that this fundamental assumption may be a gross and misleading oversimplification. It could imply that the universe is not only expanding, but is also embedded within a larger-scale flow, a cosmic current that is carrying our entire observable patch of the universe along with it. This would mean that the expansion that we observe from our vantage point is a complex and subtle combination of the global uniform expansion of the universe and this local directed flow. The task of disentangling these two effects is a major and daunting challenge for observational cosmology. This has profound and far-reaching implications for our understanding of dark energy, the mysterious and enigmatic force that is driving the accelerated expansion of the universe. In the Standard Model, dark energy is assumed to be a cosmological constant, a uniform and unchanging energy density that is inherent to the very fabric of space-time. But if dark flow is real, it could be a sign that dark energy is not so simple and straightforward. Perhaps dark energy is not a constant at all, but is instead a dynamic and evolving field that can have different values in different regions of space. A large-scale gradient in the density of this dark energy field could create a cosmic pressure difference that would drive a bulk flow of matter. This would be a truly revolutionary discovery, as it would provide the first ever direct evidence for the dynamic nature of dark energy and would open up a new and powerful window into its fundamental and unknown properties. Furthermore, the implications of the phenomenon of dark flow extend to our comprehension of the cosmic web, the large-scale and intricate structure of the universe. The formation and the evolution of this vast and beautiful structure is a delicate and intricate dance between the attractive and familiar force of gravity and the repulsive and mysterious force of dark energy. A large-scale flow would subtly but significantly alter this cosmic dance, potentially affecting the growth rate of structures and the intrinsic properties of the voids and the filaments. A complete and detailed understanding of how dark flow interacts with the cosmic web could provide critical and invaluable insights into the intricate and complex interplay between these fundamental and opposing cosmic forces. In essence, dark flow could completely alter our perception of the universe's topology, revealing a hidden and unknown geometry, a large-scale structure that is currently far beyond our observational reach. If there are indeed massive and unseen structures that are influencing the motion of galaxies from beyond the observable universe, this would mean that our current models of cosmology, which are primarily based on the observations that have been made from within our limited and perhaps unrepresentative cosmic horizon, require a significant and fundamental refinement. The unfolding and captivating story of dark flow is a powerful and humbling reminder of the provisional and ever-changing nature of scientific knowledge. It invites us to constantly and rigorously question our most basic assumptions, to reevaluate our most cherished models, and to be open to the profound and exciting possibility that the universe is far stranger and more wonderful than our current theories can possibly accommodate. The phenomenon of dark flow, this coherent and large-scale motion of galaxy clusters across the cosmic canvas, is deeply and inextricably intertwined with the more general concept of large-scale anisotropy in the universe. The cosmological principle, which has been a cornerstone and a guiding light of modern cosmology for nearly a century, posits that the universe is isotropic, meaning that it looks the same in all directions. Dark flow, if it is confirmed to be a real and physical phenomenon, would be a direct and powerful violation of this fundamental principle on the very largest of observable scales. It would imply that the universe has a preferred and specific direction, a cosmic axis along which matter is flowing. This anisotropy would not just be a local and insignificant phenomenon, but would be a fundamental feature of the universe on a grand and cosmic scale. The potential and tantalizing connections between this observed flow and other independent signs of large-scale anisotropy in the universe are a fascinating and active area of ongoing research. One intriguing hypothesis is that dark flow is a direct and gravitational response to a large-scale anisotropy in the distribution of matter itself. If there are vast unseen structures such as colossal superclusters or immense and ancient filaments that are aligned in a particular and specific way, they would create a powerful gravitational gradient that would pull all the matter in our cosmic neighborhood towards them. In this picture, dark flow is not a mysterious non-gravitational force, but is simply the natural and expected gravitational response of matter to a highly and fundamentally anisotropic mass distribution. The great challenge is that we do not observe such massive and aligned structures within our own observable universe. The ultimate source of this anisotropy, if it exists, must lie beyond our cosmic horizon. Research has indicated that the direction of the observed dark flow may be correlated with other independent observed anisotropies in the cosmos. For instance, some detailed and careful studies have found intriguing and statistically significant alignments between the direction of dark flow and certain large-scale features that are present in the cosmic microwave background, such as the axis of the quadrupole and the octopole moments of the temperature fluctuations. These are large-scale and beautiful patterns in the cosmic microwave background that are also statistically highly unlikely to be the result of random chance, and their ultimate origin is still a profound and unsolved mystery. The apparent alignment of these different and independent anisotropies could of course be a simple coincidence, but it could also be a tantalizing hint of a deeper underlying physical connection, a sign that the universe has a preferred and fundamental direction that was imprinted upon it at the very beginning of time. Moreover, the potential connection between the phenomenon of dark flow and the concept of anisotropy could provide deep and profound insights into the very early universe. If the universe underwent a period of anisotropic expansion during the inflationary epoch, it might have left behind a residual and observable anisotropy that we observe today as dark flow. This would be a truly profound discovery, as it would provide a direct and unprecedented probe of the dynamics of the process of inflation, a period of the universe's history that is otherwise completely inaccessible to direct observation. Some researchers have also suggested that exploring the deep and fundamental connection between dark flow and anisotropy could help us to understand the mysterious nature of dark energy. If dark energy itself has an anisotropic and non-uniform distribution, it could be the ultimate driving force behind the observed flow. This would be a revolutionary and paradigm-shifting idea, as it would directly challenge the standard model of a uniform and unchanging cosmological constant, and would suggest that dark energy is a much more complex and dynamic entity. The quest to understand the intricate and deep relationship between the phenomenon of dark flow and the concept of large-scale anisotropy is a journey into the deepest and most fundamental properties of our universe. A search for the hidden and beautiful symmetries and asymmetries that governed its creation and continue to shape its long and complex evolution. Distinguishing the subtle, faint, and large-scale signal of dark flow from the more common chaotic and local motions of galaxies is one of the greatest and most daunting challenges of modern observational cosmology. The universe is a dynamic and ever-changing place, and galaxies are constantly in motion, responding to the relentless and inexorable gravitational pull of their cosmic neighbors. This peculiar motion of galaxies is their individual and unique movement relative to the smooth overall and uniform expansion of the universe. It is a natural and expected consequence of the lumpy, inhomogeneous, and beautiful distribution of matter in the cosmic web. A galaxy that is located near a massive and ancient cluster will be pulled inexorably towards it, while a galaxy that is located on the edge of a large and empty void will be gently and subtly pushed away from it. These peculiar motions create a complex, chaotic, and beautiful velocity field on small and intermediate scales. Dark flow, in contrast, is hypothesized to be a much larger, more coherent, and more systematic phenomenon. A bulk motion of entire and vast regions of the universe that is not caused by the known local and mapped structures. To distinguish between these two very different phenomena, cosmologists must rely on a variety of sophisticated and powerful analytical methods. The analysis of redshift data is a primary and indispensable tool in this monumental endeavor. By meticulously measuring the redshifts of thousands upon thousands of individual galaxies, scientists can determine their velocities and can map the peculiar velocity field of the universe in 3 dimensions. They can then look for large-scale and coherent patterns in this field for coherent flows that extend over hundreds of millions of light years. Sophisticated statistical techniques, such as the analysis of the velocity correlation function, can be used to quantify the coherence of these flows and to determine whether they are statistically significant or are simply the result of random chance. Another key and complementary method is the comparison of the observed velocity field with the gravitational field that is predicted from the observed distribution of galaxies. By creating a detailed and comprehensive map of the galaxy distribution from a large-scale and deep survey, cosmologists can use the known laws of gravity to predict the peculiar velocity of any given galaxy with a high degree of accuracy. The dark flow signal would be a residual velocity that remains after the predicted gravitational influence of all the known and mapped structures has been carefully and precisely subtracted. Furthermore, cosmologists also compare the statistical properties of the observed velocity field with the detailed and precise predictions of the standard cosmological model. Large-scale and powerful supercomputer simulations of cosmic structure formation can be used to determine the expected magnitude and the coherence of the peculiar velocity flows that arise naturally from the process of gravitational instability in a universe that is governed by the standard model. If the observed flows are significantly larger or more coherent than anything that is ever seen in the simulations, it would be strong and compelling evidence for the existence of a new and unknown physical phenomenon such as dark flow. The use of different and independent observational tracers, such as galaxy clusters, type Ia, supernovae, and the kinematic Sunyaev-Zeldovich effect, provides another and powerful way to cross-check the results. If different tracers, which are all subject to different and independent systematic errors, all show evidence for a coherent flow in the same direction, it would greatly and powerfully strengthen the case for its physical reality. The ongoing and relentless investigation into these cosmic flows is a complex, multifaceted, and deeply human effort, a testament to the ingenuity and the persistence of the scientific community. It is a quest to create a dynamic and living map of the universe, a map that reveals not just the location of all the cosmic structures, but also the intricate, beautiful, and profound patterns of their motion. The significance of the phenomenon of dark flow for our understanding of the cosmic web is profound and far-reaching. The cosmic web is the grand and magnificent architecture of the universe, the intricate and beautiful filamentary network of galaxies and dark matter that spans the entire cosmos. It is the result of the gravitational evolution of the universe from the nearly uniform and featureless state of the early cosmos. The discovery of dark flow directly and powerfully challenges our understanding of the dynamics of this vast and ancient web. It suggests that the web itself may be in motion, that our entire local patch of the cosmic web is being pulled along by a cosmic current that originates from a region that lies beyond the observable universe. This would imply that the formation and the evolution of the structures that are contained within our local web, the galaxies, the clusters, the filaments, and the voids have been influenced by this external large-scale and unknown gravitational field. The cosmic microwave background radiation provides the initial conditions for the formation of the entire cosmic web. The tiny and subtle temperature fluctuations that are present in the cosmic microwave background are the primordial seeds that grew into the vast and magnificent structures that we see in the universe today. If dark flow is occurring, it suggests that there may be even larger-scale fluctuations, so-called super-horizon modes, that are not directly visible in our cosmic microwave background sky, but whose powerful gravitational influence is still being felt today. These super-horizon structures could be the ultimate source of the dark flow, and they would imply that our observable universe is just a small and perhaps not entirely representative part of a much larger and more complex cosmic structure. Moreover, the phenomenon of dark flow raises profound and difficult questions about the isotropy of the universe. The standard model of cosmology assumes that the universe looks the same in all directions. A preferred and specific direction of motion would violate this fundamental and foundational assumption and would imply that the universe has a large-scale and intrinsic asymmetry. This could have profound and far-reaching implications for the formation of the cosmic web, potentially leading to a preferred and specific orientation of the great filaments, or a non-uniform and anisotropic distribution of the massive clusters. Additionally, the phenomenon of dark flow has deep and tantalizing ties to the concept of dark energy. The accelerated expansion of the universe, which is driven by the mysterious and enigmatic force of dark energy, is a force that works against the natural and relentless gravitational collapse of structures. It is a cosmic tug-of-war that will ultimately and decisively determine the fate of the entire universe. If dark flow is indeed associated with vast and unseen structures that lie outside our observable universe, it might provide a new and unique probe of the ultimate nature of dark energy. A complete and detailed understanding of how dark flow interacts with the expansion of the universe could lead to dramatic and profound breakthroughs in our comprehension of this mysterious and powerful cosmic component. In summary, the significance of the phenomenon of dark flow in relation to the cosmic web is that it directly and powerfully challenges our most fundamental and cherished assumptions about the universe's structure, its dynamics, and its ultimate origins. It opens up new and exciting avenues for research into the ultimate nature of gravity, dark matter, and dark energy, and it forces us to confront the profound and humbling possibility that our universe is far more complex and interconnected than we have ever dared to imagine. The existence of a confirmed and verified dark flow would be a profound and direct challenge to the standard and reigning cosmological model. This model, which is known as the lambda cold dark matter model, has been remarkably and enduringly successful in explaining a vast and diverse range of cosmological observations, from the detailed and beautiful properties of the cosmic microwave background to the large-scale and intricate distribution of galaxies. It is built upon a few key and fundamental principles, including the cosmological principle, which states that the universe is homogeneous and isotropic on the very largest of scales. Dark flow, with its coherent, directed, and large-scale motion of galaxy clusters, would be a direct and powerful violation of this fundamental and foundational principle. It would imply that the universe is not as uniform and isotropic as we have long believed, and that there are large-scale and coherent structures and motions that are not accounted for in our standard and accepted model. This could mean that our universe is an integral part of a larger tilted and anisotropic structure, a cosmic landscape with a preferred and specific direction that was imprinted upon it at the very beginning of time. The implications for our understanding of the long and complex story of cosmic evolution would be immense. It would require a fundamental and radical rethinking of the initial conditions of the universe and the process of cosmic inflation. Perhaps the process of inflation was not as uniform and isotropic as we have long assumed, and it left behind a large-scale and observable asymmetry that is still visible today as dark flow. Moreover, if the phenomenon of dark flow were to be linked to the existence of new and unknown physics, it could provide deep and profound insights into the ultimate nature of dark energy. Perhaps dark energy is not a simple and unchanging cosmological constant, but is instead a more complex and dynamic entity with a non-uniform and anisotropic distribution. This could lead to a new and revolutionary understanding of the forces that are driving the accelerated expansion of the universe. Additionally, the existence of a confirmed dark flow could lead to new and exciting avenues of research in the field of cosmology, prompting detailed and ambitious investigations into the structure of the universe on the very largest of scales. It might encourage scientists to develop new and more powerful theoretical frameworks that can successfully and elegantly incorporate this strange and unexpected phenomenon, potentially leading to a more complete and unified theory of the cosmos. The unfolding and captivating story of dark flow is a powerful and humbling reminder that the process of science is a process of constant and rigorous questioning and revision. It invites us to reconsider the very boundaries of our knowledge and to be open to the profound and exciting possibility that the universe is far stranger and more wonderful than we can currently and possibly imagine. The exploration of the vast and mysterious cosmos is a journey into the unknown, a quest that is driven by our innate and deeply human curiosity to understand our place in the universe. The investigative techniques that we employ are the powerful and sophisticated tools that allow us to embark on this monumental journey to gather precious data from the farthest and most ancient reaches of space and time, and to piece together the grand and magnificent story of cosmic evolution. Remote sensing, the collection of data from a great distance, is the true workhorse of modern astronomy. Telescopes, both on the ground and in the unforgiving environment of space, are our powerful and extended eyes on the universe, capturing the faint and ancient light from distant stars and galaxies and revealing their deepest and most hidden secrets. Spectroscopy. The detailed and careful analysis of this light is our cosmic Rosetta Stone, allowing us to decipher the chemical composition, the temperature, and the motion of all the celestial objects. Computer modeling and sophisticated simulations are our virtual laboratories, allowing us to explore the full and complex consequences of our most cherished theories, and to create beautiful and detailed digital universes that we can study in exquisite and unprecedented detail. Direct observation through the use of robotic and autonomous space missions is our way of reaching out and physically touching the cosmos. The intrepid rovers on the surface of Mars, the sophisticated probes that are currently orbiting Jupiter and Saturn, and the ambitious spacecraft that have visited distant asteroids and comets have given us an intimate close-up and breathtaking view of our solar system neighbors. And the recent and revolutionary advent of gravitational wave astronomy has opened up a completely new and powerful window on the universe, allowing us to listen to the beautiful and intricate symphony of space-time itself. In the context of the great mystery of dark flow, a powerful and synergistic combination of all of these techniques is being employed to unravel its deepest and most hidden secrets. The precise and detailed measurement of the cosmic microwave background, the careful and painstaking analysis of vast redshift surveys, the intricate and beautiful mapping of gravitational lensing, and the use of sophisticated and powerful computational models are all contributing to our understanding of this enigmatic and fascinating phenomenon. Each new and more precise observation, each new and more powerful simulation provides another and crucial piece of the puzzle, bringing us ever closer to a definitive and final answer. Redshift surveys are a particularly powerful and indispensable tool in this ongoing investigation. By mapping the three-dimensional distribution and the motion of millions upon millions of individual galaxies, these ambitious and large-scale surveys are creating an unprecedentedly detailed and beautiful picture of the cosmic web. Within this intricate and breathtaking picture, the faint, subtle, and coherent signal of dark flow can be searched for, and if it exists, can be characterized with a high degree of precision. Statistical methods are the absolute key to this monumental search. The universe is a noisy and chaotic place, and the signal of dark flow is expected to be subtle and faint. Sophisticated and powerful statistical techniques, including the use of modern and advanced machine learning algorithms, are needed to extract this faint and elusive signal from the overwhelming and ever-present background of random peculiar motions and unavoidable observational uncertainties. The challenges are immense, but the potential and profound rewards are even greater. The ongoing and relentless research into the phenomenon of dark flow is a testament to the power of the scientific method, a collaborative, international, and deeply human effort to push the boundaries of our knowledge and to achieve a deeper and more complete understanding of the universe that we inhabit. The ongoing research into the phenomenon of dark flow is a vibrant, dynamic, and rapidly evolving field with new and more precise studies and new and richer data constantly refining our understanding of the cosmos. The current and most ambitious projects are focused on creating larger and more precise maps of the peculiar velocity field of the universe using a diverse and powerful variety of observational techniques. The ultimate goal of these projects is to either confirm the existence of dark flow with a high and irrefutable level of statistical significance, or to show that the observed motions can be explained entirely and satisfactorily within the framework of the standard cosmological model. The future of dark flow research is incredibly bright, with a new and more powerful generation of telescopes and surveys that are poised to completely revolutionize the field. The Vera C. Rubin Observatory, with its ambitious legacy. Survey of space and time will map the entire southern sky with an unprecedented depth and speed, providing a true treasure trove of data for studying the large-scale motions of the universe. The square-kilometer array, when it is completed, will create the most detailed and comprehensive maps of the distribution of hydrogen gas in the universe, providing a new and completely independent tracer of the cosmic velocity field. And the James Webb Space Telescope will allow us to peer deeper into the cosmos than ever before, revealing the earliest and most formative stages of galaxy formation and their deep and fundamental connection to the large-scale structure of the universe. These observational advances will be complemented by equally impressive progress in the fields of theoretical cosmology and computational simulations. As our understanding of the mysterious nature of dark matter, dark energy, and the physics of the very early universe improves our models of cosmic structure, formation will become more sophisticated, more powerful, and more predictive. This will allow for more rigorous and more powerful tests of the dark flow hypothesis and for a deeper and more profound exploration of its potential and far-reaching implications. The international and collaborative nature of this research is absolutely essential for its success. The challenges are simply too great for any single research group or any single nation to tackle alone. It is through the collective and synergistic efforts of scientists from all around the world, sharing their precious data, their unique expertise, and their bold and creative ideas that we will ultimately unravel the deep and profound mysteries of dark flow. Recent studies have continued to yield intriguing, though still not definitive results. Some detailed and careful analyses of the latest and most precise data from the Planck satellite and the largest-scale galaxy surveys have found continued and tantalizing evidence for a bulk flow, though its magnitude and its direction may differ from the initial findings. Other and equally careful studies have found no significant signal highlighting the ongoing and persistent challenges and uncertainties that are inherent in these incredibly difficult measurements. The debate is likely to continue for some time to come, but it is a healthy and a productive debate, one that is pushing the field forward and is leading to a deeper and more nuanced understanding of the universe's dynamics. The intersection of dark flow research with the detailed and beautiful study of the cosmic microwave background remains a particularly fruitful and exciting area of ongoing investigation. The search for subtle and characteristic correlations between the observed flows and the large-scale anisotropies that are present in the cosmic microwave background could provide a smoking gun for a primordial origin of dark flow, a deep and fundamental connection to the physics of the very early universe. The future directions for research on dark flow are clear and well-defined. We need more data, better and more powerful models, and new and more creative ideas. The observational and the theoretical tools are in place to make significant and dramatic progress in the coming years. The broader context of space exploration is one of relentless and insatiable curiosity, of a deep and innate human need to understand our place in the cosmos. The great mystery of dark flow is an integral and important part of this grand and noble quest, a tantalizing and beautiful hint of a universe that is far larger, stranger, and more wonderful than we have ever dared to imagine. The philosophical implications of this research are profound and far-reaching. It directly and powerfully challenges our anthropocentric biases and forces us to confront the profound and humbling possibility that our universe is just a small and perhaps insignificant part of a much larger, interconnected, and perhaps eternal reality. The study of dark flow is not just about measuring the motion of distant and ancient galaxies. It is about expanding the very horizons of our knowledge and our imagination. The connection between the phenomenon of dark flow, the mystery of dark matter, and the enigma of dark energy is a deep, complex, and beautiful one. These three dark components of the universe are not separate, isolated, and disconnected mysteries, but are instead interconnected and interwoven aspects of a single overarching and magnificent puzzle. Dark flow, if it is caused by the gravitational pull of vast and unseen structures, could provide a new and powerful way to map the distribution of dark matter on the very largest of scales. It could reveal the existence of superhorizon structures that are otherwise completely and forever inaccessible to us. The study of dark flow could also provide deep and profound insights into the early universe, the extreme and exotic conditions that existed shortly after the Big Bang. If dark flow is a remnant of the process of cosmic inflation, it could provide a unique and unprecedented window into the physics of this primordial and formative epoch. The ultimate fate of the universe is inextricably and forever linked to the properties of dark energy. Dark flow, by providing a new and powerful probe of the large-scale dynamics of the universe, could help us to better understand the ultimate nature of this mysterious and powerful force and to make more accurate and reliable predictions about the ultimate destiny of our cosmos. The unfolding and captivating story of dark flow is a powerful and humbling reminder that we are still in the very early and tentative stages of our exploration of the universe. There are vast, uncharted territories of knowledge that are waiting to be discovered. The journey is long and challenging, but the potential rewards are immense, a deeper and more complete understanding of the universe that we inhabit and of our place within its grand, beautiful, and magnificent design. The grass is green, or so it seems. In the reality you perceive, the blades of grass in a sunlit field reflect a particular wavelength of light, and the three types of color receptors in your eyes, working in concert with the intricate neural architecture of your brain, interpret this signal as green. But this is not the color of the grass itself. To a dog, with only two types of color receptors, that same field of grass appears yellowish-gray. To a bee, which can see in the ultraviolet spectrum, the grass is part of a complex, multicolored tapestry of patterns that are completely invisible to us. So, what is the true color of the grass? The question itself is flawed. Color is not a property of the object. It is a perception, a subjective experience created in the mind of the observer. Before you look at it, the grass is not green, nor is it beige. It simply is. A complex molecular structure that reflects a spectrum of electromagnetic radiation. The same is true for the rest of the world. The ground beneath your feet feels solid, unyielding. But if you were to zoom in, to journey down into the subatomic realm of the atoms that make up the floor, you would find that it is, in fact, almost entirely empty space. The nucleus of an atom is a tiny, dense point, and the electrons that orbit it are even smaller, separated by vast, cosmic-scale voids. The solidity you feel is not a property of the matter itself. It is an illusion, a powerful and convincing one, created by the repulsive force of the electrical fields of the atoms in your body pushing against the electrical fields of the atoms in the floor. You are not physically touching the floor. You are energy, interacting with energy. The screen you are looking at right now, the sound of my voice in your ears, the feeling of the chair supporting your body, all of these are, at their core, just electrical signals. Complex patterns of information being processed and interpreted by your brain. Your brain has never seen the light from the screen. It has never heard the sound waves from the speaker. It has never touched the fabric of the chair. It has only ever known the language of electrical impulses, the silent electrochemical chatter of its own internal world. The reality you are experiencing right now is a high-resolution, multi-sensory, and perfectly rendered simulation. A world picture that has been constructed for you by you, in the dark, silent theater of your own mind. So, if everything you have ever seen, ever felt, ever thought, is a mental construction, a story that your brain is telling itself, then what is the difference between this waking reality and the reality of a dream? Are you dreaming with your eyes open, or are you truly awake? Imagine you are standing in a large, open field, and you and a friend are holding opposite ends of a long, taut rope. You can feel the tension in the rope, a direct, physical connection that spans the distance between you. Every subtle tug, every gentle release that your friend makes at their end is transmitted through the rope and is felt by you, almost instantaneously. This is our classical, intuitive understanding of how the world works. It is a world of locality, a world where things can only influence each other through direct, physical contact or through a clear, unbroken chain of cause and effect. A push causes an object to move. A sound wave travels through the air. A signal is transmitted along a wire. This is the world of Isaac Newton, a world that is orderly, predictable, and grounded in common sense. But now, imagine something far stranger. You and your friend drop the rope. There is nothing between you but the empty air. And yet, when your friend makes a tugging motion, you instantly feel a pull in your own hands. There is no rope, no string, no visible connection of any kind. Your friend could be on the other side of the field or on the other side of the planet, and the effect would be the same, instantaneous. This is a world that defies our classical intuition. It is a world that is non-local, and it is a world that, according to the strange and beautiful laws of quantum mechanics, is the true underlying reality of our universe. At the smallest, most fundamental scales of existence, particles can become entangled, linked in a way that transcends the normal boundaries of space and time. This is not like a wireless signal from your phone, which travels at the speed of light and can be detected and traced. This is a deeper, more mysterious connection, a spooky action at a distance. As a skeptical Albert Einstein famously called it, if you take a single atom and you split it into two entangled parts, and you send these two parts to opposite ends of the Earth, you will find that a measurement on one part will instantly influence the state of the other. There is no signal, no delay, no physical link of any kind. It is as if the two particles are not two separate things, but are two aspects of a single, unified, and non-local reality. It is as if separation itself is an illusion. And if the universe behaves in this strange, non-local way at its very core, then what does that say about the macroscopic world of our own experience? Is the solid, separate, and seemingly local world we see around us just a shadow, a projection of a much deeper, more unified, and more mysterious reality? Is it possible that all the matter and all the energy in the universe, the distant stars and the atoms in your own body, are all part of a single, vast, and interconnected quantum system? This profound and unsettling idea, that the universe may not be what it seems, that the very fabric of our reality may be an illusion, is a concept that has begun to migrate from the fringes of theoretical physics and philosophy into the heart of mainstream scientific inquiry. If the separation between objects is not as real as it appears, if the universe is, at its core, a holistic and non-local entity, then what is the true nature of this underlying, unified reality? One of the most radical and yet scientifically plausible of these ideas is the holographic principle. This is a concept that emerged from the deep theoretical study of black holes, and it suggests that all the information contained within a three-dimensional volume of space can be, in a sense, encoded on its two-dimensional boundary. It is as if our entire three-dimensional universe is a kind of hologram, a complex three-dimensional projection of information that is stored on a distant two-dimensional surface at the edge of the cosmos. In this picture, the world of our experience, with its depth, its solidity, its separation of objects in space, is not the fundamental reality. It is an emergent, and in some sense, illusory, phenomenon, a holographic image generated from a deeper, more fundamental, and non-local informational reality. Another, and perhaps even more unsettling, possibility is the simulation hypothesis. This is the idea that our entire universe, with all its history, all its laws, and all its inhabitants, is a sophisticated computer simulation, a virtual reality created by a far more advanced, post-human civilization. The laws of physics are not fundamental truths of nature. They are the programmed rules of the simulation. The particles that make up our world are not solid, physical things. They are pixels on a cosmic screen. And our own consciousness, our thoughts, our feelings, our very sense of self, may be nothing more than the product of a complex, artificial intelligence running on a vast, and as yet unimaginable, computational substrate. This is an idea that can feel like a dizzying, philosophical vertigo. And yet, it is an idea that is being taken seriously by a growing number of physicists and philosophers, as it provides a potential explanation for a number of the strange and seemingly fine-tuned features of our own universe. The fact that the universe seems to be governed by a set of elegant mathematical laws, the fact that there seem to be fundamental, discrete units of space, time, and energy at the Planck scale. The strange, observer-dependent nature of quantum reality, all of these are features that would be natural, and even expected, in a simulated reality. The universe, in this view, is a grand and beautiful video game, and we are, perhaps, just non-player characters, with no knowledge of the game's creators, or of the true, base reality that lies outside the simulation. Or perhaps, our universe is part of an even grander and more complex structure, a multiverse. The theory of eternal cosmic inflation suggests that our universe may be just one bubble in an infinite, self-reproducing cosmic foam of other universes, each with its own, potentially different, physical laws. The many worlds interpretation of quantum mechanics suggests that every quantum event splits the universe into a branching tree of parallel realities. In this vast, and perhaps infinite, multiverse, every possibility is realized. There are an infinite number of versions of you, living out an infinite number of different lives. In this picture, our sense of a single, unique reality is an illusion born of our limited perspective, our confinement to a single branch of the universal wave function. We feel separate, but we are, in fact, part of a much larger and much stranger whole. All of these ideas, the hologram, the simulation, the multiverse are, for now, on the speculative frontiers of science, but they are all pointing in the same profound direction. They are all suggesting that the universe we perceive with our senses, the world of separate, solid, and local objects, is not the ultimate reality. It is a shadow, a projection, a single frame in a much larger and much more mysterious cosmic movie. And the true nature of that movie, the source of its light, the identity of its director, remains the deepest and most beautiful of all scientific questions. The story of our modern scientific grapple with the nature of reality begins, in many ways, with a single, seminal, and deeply reluctant paper. In 1935, Albert Einstein, along with his two younger colleagues, Boris Podolsky and Nathan Rosen, published a paper that was intended to be a death blow to the strange and unsettling new theory of quantum mechanics. They titled it, with a characteristically academic and understated flair, Can quantum mechanical description of physical reality be considered complete? But the question it posed, and the thought experiment it contained, would ignite a debate that would rage for decades and would ultimately lead to a profound and revolutionary transformation in our understanding of the universe. Einstein, by this time, was the elder statesman of physics, a global icon who had single-handedly overthrown the Newtonian universe with his theories of relativity. And the universe he had revealed was a beautiful, elegant, and deeply orderly one. It was a grand cosmic clockwork, a universe of smooth, curved space-time, of deterministic laws, of a reality that was objective, independent, and, in a word, real. But quantum mechanics, the new theory that had been developed by a younger generation of physicists, was a direct affront to this classical common-sense worldview. It was a theory that was built on a foundation of randomness or of probability, of uncertainty. It suggested that a particle could be in many places at once, that its properties were not defined until they were measured, that the universe, at its core, was a game of cosmic dice. And Einstein, famously, did not believe that God played dice. For centuries, the worldview of physics had been that of local realism. It was a worldview with two simple and deeply intuitive pillars. The first was locality, the idea that an object can only be influenced by its immediate surroundings. An action here cannot have an instantaneous effect on something over there. All influences, all information must travel through space at a finite speed, a speed that is limited by the speed of light. This was a cornerstone of Einstein's own theory of special relativity. If you are a NASA engineer and you want to send a command to the Mars rover, you must wait at least 3 minutes for your signal to travel across the intervening space. There is no way around this cosmic speed limit. The second pillar was realism, the belief that the objects of the physical world have definite, objective properties. Whether we are observing them or not, a rock is a rock. It has a definite position, a definite mass, a definite shape. The moon, as Einstein was fond of saying, is still there, even when nobody is looking at it. This belief in an objective, observer-independent reality was the very foundation of the scientific method. Together, these two principles, of locality and realism, formed a sturdy and reassuring framework for understanding the world. They were the bedrock of the classical physics of Newton and Maxwell, a physics that had been so spectacularly successful in explaining everything from the fall of an apple to the motion of the planets. It was a picture of a predictable, rational, and transparent cosmos. And then, in the early 20th century, as scientists began to probe the strange new world of the atom, this beautiful classical picture began to unravel. The unraveling began with a series of experiments that revealed a world that was not just strange, but seemingly paradoxical. The classical picture of matter was that of tiny, solid, billiard ball-like particles. But when scientists performed the double-slit experiment, they found that a single electron, when not observed, behaves like a wave, passing through both slits at once and interfering with itself. The very nature of the electron's reality seemed to depend on the context of the experiment, on the question that was being asked of it. This was the wave-particle duality, the central, and still mysterious, paradox of the quantum world. But even stranger was the implication that the act of observation itself seemed to play a crucial and creative role in shaping reality. It was as if the electron's properties were not defined, were not real until they were measured. This was a direct challenge to the principle of realism. And then came the phenomenon of entanglement, a direct challenge to the principle of locality. The theory of quantum mechanics predicted that two particles could become linked in such a way that their properties would remain correlated, no matter how far apart they were separated. A measurement on one particle would have an instantaneous effect on the other, a spooky action at a distance that seemed to violate the cosmic speed limit. To Einstein, this was a clear sign that the theory was incomplete. There had to be a deeper, more classical reality hiding beneath the probabilistic and seemingly non-local facade of quantum mechanics. There had to be hidden variables, unknown properties of the particles that were determined at the moment of their creation, and that carried with them the instructions for how to behave when they were later measured. This would restore both realism and locality. The famous EPR paper of 1935 was the most sophisticated and powerful articulation of this argument. It was a thought experiment and Gedankenexperiment designed to expose the absurdity and the incompleteness of the quantum mechanical worldview. It imagined a pair of entangled particles, created at a central source and sent flying off in opposite directions. By measuring the position of one particle, you could, with perfect certainty, predict the position of the other, without in any way disturbing it. And by measuring the momentum of the first particle, you could predict the momentum of the other, since you could, in principle, know both the precise position and the precise momentum of the second particle. Both of these properties must be simultaneously real. But this directly contradicted another of the strange principles of quantum mechanics, Heisenberg's uncertainty principle, which states that it is impossible to know both the position and the momentum of a particle with perfect precision at the same time. The conclusion, for EPR, was inescapable. Quantum mechanics must be an incomplete theory. It was just a statistical approximation of a deeper, more fundamental, and locally realistic reality. But Niels Bohr, the great Danish physicist and the philosophical father of the quantum revolution, disagreed profoundly. He argued that the EPR paper was based on a fundamental misunderstanding of the nature of quantum reality. For Bohr, a quantum system, like an entangled pair of particles, is an indivisible whole. You cannot speak of the properties of one particle independently of the other, or independently of the measuring device that you use to observe them. Reality is not a collection of separate, independent things with pre-existing properties. It is a holistic, contextual, and relational phenomenon. The properties of a particle are not revealed by a measurement. They are created in the act of measurement. The debate between Einstein and Bohr was one of the great intellectual duels of the 20th century. It was a clash of two, fundamentally different, and seemingly irreconcilable worldviews, and for decades, it remained a purely philosophical debate, a matter of taste and interpretation. There seemed to be no way to experimentally distinguish between the two pictures. And then, in the 1960s, a quiet, unassuming, and brilliant physicist named John Stuart Bell, working in his spare time at the CERN laboratory in Geneva, found a way. John Bell was not a man who was looking for a revolution. He was a particle physicist, a man who was grounded in the practical and often messy world of building and understanding particle accelerators. But in the quiet of his own mind, he was haunted by the deep, unresolved, and philosophical questions that lay at the heart of quantum mechanics. He was particularly intrigued by the work of the American physicist David Bohm, one of the few who had taken Einstein's skepticism seriously and had developed a fully fledged hidden variable theory, a theory that could reproduce all the predictions of standard quantum mechanics, but which was built on a foundation of a deeper, deterministic, and non-local reality. Bohm's theory was largely ignored by the mainstream physics community, but for Bell, it was a proof of principle. It showed that hidden variable theories were not just a philosophical fancy, they were a real mathematical possibility. This planted a seed in Bell's mind. Was there a way to experimentally test the very idea of local realism itself? Was there a way to devise an experiment that would give one result if Einstein's classical common-sense worldview was correct, and a different result if the strange, non-local, and probabilistic world of quantum mechanics was the true reality. After months of intense and often solitary work, Bell found the answer. His insight was a stroke of pure genius. He realized that while a simple experiment with a single pair of entangled particles could not distinguish between the two worldviews, a series of experiments, with the detectors set at different and randomly chosen angles, could. He derived a now famous mathematical inequality. Bell's inequality, which set a strict upper limit on the amount of statistical correlation that could be observed between the measurements on the two separated particles. If the world was governed by the principles of local realism, quantum mechanics, on the other hand, predicted that for certain specific settings of the detectors, this inequality would be violated. The correlations would be stronger than any local realistic theory could possibly explain. Bell had, in a single, beautiful, and profound paper, transformed the Einstein-Bohr debate from a matter of philosophy into a matter of experimental, empirical fact. The universe had to make a choice. It could be local and realistic, in which case Bell's inequality would be obeyed, or it could be quantum mechanical, in which case the inequality would be violated. It could not be both. To understand the essence of Bell's theorem, imagine a game. You have two separated players, Alice and Bob. A central source sends each of them a particle from an entangled pair. Alice and Bob can each choose to measure their particle in one of two different ways. Say, by passing it through a polarizer that is oriented either vertically or horizontally. After they have made their measurements, they get together and compare their results. Bell's inequality is a statement about the statistical correlations between their results, averaged over many runs of the experiment. If the particles are like classical objects, with predetermined, hidden properties, then there is a limit to how strongly their results can be correlated. But if they are quantum mechanical, if they are part of a single, non-local, entangled state, then their results can be more strongly correlated than any classical theory would allow. It is as if they are part of a team that is so perfectly coordinated that they can win the game more often than the classical rules would permit. Bell's work, when it was published in 1964, was initially met with a deafening silence. The technology to actually perform such a delicate and precise experiment did not yet exist, and the mainstream physics community, for the most part, had accepted the pragmatic Copenhagen interpretation and had moved on from what they saw as the sterile philosophical debates of the founding generation, but the seed had been planted. And in the early 1970s, a young and stubbornly independent-minded graduate student at Columbia University named John Clauser stumbled upon Bell's paper and decided that he was going to be the one to put it to the test. John Clauser was a man who was not afraid to challenge the orthodoxy. While his professors and his peers were focused on the more fashionable and well-funded frontiers of particle physics, Clauser was drawn to the deep, foundational, and often overlooked questions that lay at the heart of quantum mechanics. When he read Bell's paper, he saw not just a theoretical curiosity, but a profound, experimental challenge. He wrote to Bell, and their correspondence solidified his resolve. He was going to build an experiment to test Bell's inequality. Together with his student, Stuart Friedman, Clauser designed and built the first practical experimental test of Bell's theorem. The experiment, conducted at the University of California, Berkeley, in 1972, was a masterpiece of shoestring ingenuity and experimental grit. It involved creating pairs of entangled photons by exciting calcium atoms and then measuring the correlations in their polarization as they flew off in opposite directions. The setup was delicate. The signals were weak, and the technical challenges were immense. But after months of painstaking work, they had their result. The data was clear, and it was unambiguous. Bell's inequality was violated. The correlations between the photons were stronger than any local. Realistic theory could explain. The predictions of quantum mechanics were correct. Einstein, it seemed, was wrong. The universe was, in some deep and fundamental way, non-local. This was a groundbreaking result, a landmark in the history of physics, but it was not the final word. Clauser's experiment, as brilliant as it was, had several potential loopholes, subtle and sometimes contrived, ways in which a determined, local realist could still explain the result. The locality loophole, for example, was the possibility that the two detectors, or the choice of their settings, could have somehow communicated with each other during the experiment, at a speed less than or equal to the speed of light, to coordinate their results. The detection loophole was the fact that the photon detectors were not perfectly efficient. They missed many of the photons. It was possible, in principle, that the detectors were only detecting a biased and unrepresentative subsample of the photons, the ones that just happened to be correlated in a quantum mechanical way. It was the French physicist Alain Aspect who, in the early 1980s, took on the challenge of closing the locality loophole. Working at the Institute of Optics in Orsay, France, Aspect and his team designed a series of increasingly sophisticated and elegant experiments. Their key innovation was the use of a high-speed acousto-optical switch that could change the orientation of the polarizers while the photons were in flight, after they had already left the source. The choice of which measurement to perform on each photon was made so quickly and so late that there was simply not enough time for any signal, traveling at the speed of light, to communicate that choice to the other side of the experiment before the other measurement was completed. The two measurement events were space-like separated, in the language of relativity, meaning they were causally disconnected. The results of Aspect's experiments were a stunning confirmation of Clauser's earlier work. Bell's inequality was violated, and by an even greater margin. The locality loophole was, for all practical purposes, closed. The spooky action at a distance was real, but the work was still not done. There were other, more subtle, loopholes to close. And it was the Austrian physicist Anton Zeilinger who, in the 1990s and 2000s, would take the experimental tests of Bell's theorem to a new level of rigor, of scale, and of conceptual beauty. Zeilinger is a master of experimental quantum optics, a physicist with a deep philosophical bent and a flair for the dramatic. One of his team's most famous experiments, conducted in 2007, was a Bell test that was performed not in a laboratory, but across the open air between two of the Canary Islands, La Palma and Tenerife, a distance of 144 kilometers. This was a feat of immense technical difficulty, requiring the precise alignment of telescopes and the transmission of single, entangled photons through the turbulent atmosphere. The sheer scale of the experiment was a powerful and visceral demonstration of the reality of non-locality. But Zeilinger's most profound contribution was his ingenious solution to the freedom of choice loophole. This is the most philosophical of all the loopholes, the last refuge of the determined local realist. It is the idea that the choice of which measurement to perform is not truly free or random, but is itself determined by some hidden common cause in the shared past of the experiment, a cause that also determines the properties of the entangled particles. It is a form of superdeterminism, a grand conspiracy of nature that perfectly mimics the predictions of quantum mechanics. To close this loophole, you need a source of randomness that is so ancient, so distant, and so causally disconnected from the experiment that it could not possibly be part of such a conspiracy. And Zeilinger found the perfect source: distant quasars. In an experiment conducted in 2018, his team used the light from two ancient quasars on opposite sides of the sky, whose light had been traveling towards the Earth for billions of years. to control the settings of their polarizers in a Bell test. The choice of whether to measure the polarization of a photon vertically or horizontally was determined, in real time, by whether the incoming light from a quasar was red or blue. Any hidden variable that was trying to coordinate this experiment would have had to set its plan in motion billions of years ago, long before the Earth, or even our solar system, had formed. The results, once again, were a perfect confirmation of quantum mechanics. The freedom of choice loophole was closed. The last desperate argument for local realism was laid to rest. In 2022, the Nobel Prize in Physics was jointly awarded to John Clauser, Alain Aspect, and Anton Zeilinger for their pioneering and collectively definitive experimental work on quantum entanglement. The prize was a long overdue recognition of a series of experiments that have not just confirmed one of the strangest predictions of a scientific theory, but have fundamentally and irrevocably changed our very understanding of the nature of physical reality. The universe is not local, and it is not, in the classical sense, real. The world of our everyday, common sense intuition is an illusion, a macroscopic approximation of a much deeper, much stranger, and much more beautifully interconnected quantum reality. The definitive, experimental confirmation of quantum non-locality, the reality of spooky action at a distance, is a discovery of such profound and mind-altering significance that we are still, as a scientific and philosophical culture, struggling to fully grasp its implications. It is a discovery that shatters the very foundations of our classical, mechanistic worldview and forces us to confront a universe that is far more holistic, more interconnected, and more mysterious than we ever imagined. If the principle of locality is false, if an action here can have an instantaneous effect on something over there, without any signal passing through the intervening space, then our very concept of space as the medium that separates and insulates objects is called into question. Space, it seems, does not separate entangled particles. It is simply the arena in which their pre-existing non-local connection is manifested. This suggests that there may be a deeper level of reality, a subspace or a pre-space, that is not governed by the familiar geometry of our three-dimensional world, a level of reality where everything is, in a sense, in immediate contact with everything else. This is the idea of a holographic universe, a concept that, as we have seen, has its roots in the physics of black holes. It is the idea that our familiar three-dimensional world is a kind of projection, a holographic image of information that is stored on a distant, two-dimensional surface. In this picture, the non-locality of entanglement is no longer a mystery. The two entangled particles are not really separated by a vast distance in three-dimensional space. They are at the deeper informational level of the hologram surface, right next to each other. Their instantaneous connection is just a reflection of their proximity on the underlying holographic plate. This is a radical and deeply counterintuitive idea, but it is one that is being taken very seriously by many of the world's leading theoretical physicists, as it offers a potential path towards a unified theory of quantum gravity. The failure of realism, the fact that a particle's properties are not defined until they are measured, is equally profound. It suggests that the universe, at its core, is not a world of things, but a world of information. This is the essence of John Wheeler's it from bit hypothesis. The physical reality of a particle, its itness, arises from the informational bitness of a series of yes-no questions that are answered in the act of measurement. A particle is not a solid, pre-existing object. It is the outcome of a cosmic computation. This informational view of reality provides a natural framework for understanding the universe as a vast quantum computer. The laws of physics are the software, the rules that govern how the information is processed. The quantum fields that fill all of space are the hardware, the computational substrate. and the evolution of the universe is the running of a grand cosmic program. This, in turn, leads us to the most unsettling, and yet strangely logical, of all possibilities, the simulation hypothesis. If the universe is, at its core, informational and computational, then is it not possible, and perhaps even probable, that our entire reality is a simulation, a virtual world created by a far more advanced intelligence? The philosophical implications of this new, non-local and informational worldview are immense. It challenges our deep-seated sense of individuality and separation. If the universe is a single, entangled, holographic, and informational whole, then the boundaries between ourselves and the world, between mind and matter, between the observer and the observed, are not as solid as they appear. We are not separate, isolated beings, looking out at an external world. We are an integral and participatory, part of a single, vast, and co-creative cosmic process. Our consciousness is not just a passive witness. It is an active participant in the ongoing creation of reality. The discoveries of Bell, of Clauser, of Aspect, and of Zeilinger have not just given us a new picture of the universe. They have given us a new picture of ourselves. They have shown us that the world of our everyday, classical intuition is a beautiful and useful illusion, a user-friendly interface that hides a much deeper, much stranger, and much more beautifully interconnected quantum reality. And the great adventure of 21st century science is to continue to peel back the layers of this illusion, to explore the depths of this hidden reality, and to learn to live in a way that is worthy of the profound, mysterious, and deeply magical universe we are now beginning, for the very first time, to truly see. The history of video games, from the simple black and white pixels of Pong to the breathtakingly photorealistic, ray-traced landscapes of today, is a story of an exponential and seemingly inexorable increase in computational power and graphical fidelity. In 1972, the peak of interactive entertainment was two: simple, digital paddles and a bouncing, square ball. 50 years later, a mere blink of an eye in the grand sweep of human history, we can now create and explore digital worlds that are, in many ways, indistinguishable from reality. We can walk the streets of a bustling, virtual city. We can fly through the clouds of a simulated sky. We can feel the sun on our skin and the wind in our hair in a fully immersive, virtual reality environment. The line between the real and the virtual is becoming increasingly blurred. And if this is the progress we have made in just half a century, what will be possible in 1,000 years? In 1,000,000? The logical endpoint of this trajectory is a future where simulated realities are not just indistinguishable from base reality, but are far more numerous. An advanced, post-human civilization, with access to a planetary, or even stellar, scale of computational resources, could, in principle, create a vast number of ancestor simulations, highly detailed and perfectly realistic. Simulations of their own evolutionary past, populated by artificial conscious beings who have no idea that they are living inside a computer program. This is the foundation of Nick Bostrom's famous simulation argument. It is not a proof that we are living in a simulation, but a powerful probabilistic argument that forces us to confront a startling trilemma. Bostrom argues that one of the following three propositions must be true. First, it is possible that almost all civilizations at our level of technological development go extinct before they reach the post-human stage, the stage where they have the computational capacity to run such simulations. This is the great filter hypothesis, the idea that there is some almost insurmountable hurdle that prevents the emergence of long-lived, technologically advanced civilizations. Second, It is possible that almost all post-human civilizations lose interest in running ancestor simulations. Perhaps they find it ethically problematic, or perhaps they have moved on to other, more interesting and less computationally expensive forms of entertainment or scientific inquiry. Or third, if the first two propositions are false, if a significant number of civilizations do survive to a post-human stage, and they do choose to run a large number of ancestor simulations, then the number of simulated beings, like us, would be vastly, astronomically larger than the number of real, non-simulated beings. And if that is the case, then a simple, statistical argument suggests that it is overwhelmingly probable that we are one of the simulated beings, not one of the real ones. The simulation hypothesis is a modern, scientific, and computational version of some of the oldest and most profound philosophical questions. It is Plato's cave, updated for the digital age. It is Descartes' evil demon, reimagined as a cosmic programmer. It is the Buddhist concept of Maya, the idea that the world of our sensory experience is a powerful and convincing illusion. But unlike its philosophical predecessors, the simulation hypothesis is not just a metaphysical speculation. It is a concept that is, in principle, testable. If our universe is a simulation, then it must be running on some kind of computational substrate, and that substrate must have a finite resolution, a finite processing speed. This could manifest itself in the very laws of our own physics. The existence of a smallest possible unit of length, the Planck length, and a smallest possible unit of time. The Planck time could be seen as the pixel size of the cosmic simulation. The fact that the universe seems to be governed by a set of elegant mathematical laws could be a sign that we are living in a world that has been coded. And the strange, observer-dependent nature of quantum reality. The fact that particles do not have definite properties until they are measured is eerily similar to the way that a modern video game renders its graphics. The game engine does not calculate the state of the entire game world all at once. It only renders the parts of the world that the player is currently looking at, a form of lazy computation that saves on processing power. Perhaps the universe does the same. Perhaps the wave function collapse is the universe's rendering engine, creating reality on the fly as it is needed in response to the requests of our observations. The search for these glitches in the matrix, for the subtle, telltale signs of an underlying computational reality, is a new and exciting, if highly speculative, frontier of scientific inquiry. Physicists are looking for subtle violations of the symmetries of space-time, for patterns in the cosmic microwave background that might look like the raster scan of a cosmic television screen, for any hint that our reality is not as smooth, as continuous, and as real as it appears. Whether we will ever find such definitive proof is an open question. But the simulation argument itself is a powerful and valuable tool for thought. It forces us to question our most basic and unexamined assumptions about the nature of reality. It encourages us to maintain a stance of intellectual humility, to recognize that the world may be far stranger and far more complex than our current scientific and philosophical models can accommodate. And it raises a final, and perhaps unanswerable, set of questions. If we are living in a simulation, who are the simulators? What is their nature? What is their purpose in creating a universe like ours? Are we a scientific experiment, a work of art, a historical reenactment, or are we just a piece of entertainment? A very advanced and very immersive video game for beings whose intelligence and whose motives are forever beyond our comprehension. The silence of the cosmos, the great silence of the Fermi paradox, takes on a new and chilling meaning in this context. Perhaps the reason we have not heard from any other advanced civilizations is because they are all, like us, just characters in a simulation, with no way to communicate with the real world outside. Or perhaps, even more chillingly, our simulation is the only one that has been allowed to run this far. Perhaps the architects are watching and listening and waiting.